Approximately 100 million years ago, during the mid-Cretaceous period, the landmasses of what is now North America were divided by a vast interior seaway. This body of water, known as the Western Interior Seaway, stretched from the Arctic Ocean in the north to the Gulf of Mexico in the south, bisecting the continent along a north to south axis for tens of millions of years. At its widest, it spanned roughly 1,000 kilometers. At its deepest, it reached several hundred meters below the surface. It was warm, shallow, relative to modern oceans, and saturated with life at a density that present-day marine environments rarely approach. The conditions that produced this seaway were not incidental. Global temperatures during the Cretaceous were substantially higher than today, with polar ice largely absent and sea levels elevated by an estimated 100 to 200 meters above current baselines. Tectonic activity contributed to the flooding of continental interiors across multiple regions of the planet. The result was a network of shallow epicontinental seas, bodies of water resting not on oceanic crust, but on the submerged margins of continents. These environments were chemically productive, thermally stable across long seasonal cycles, and nutrient-rich in ways that supported extraordinarily large organisms across multiple trophic levels. The Western Interior Seaway was among the most ecologically dense of these environments. Its warm waters supported extensive populations of ammonites, shelled cephalopods with coiled or straight shells that ranged from a few centimeters to well over a meter in diameter. These organisms functioned as a foundational prey base, present in such volume that they structured the feeding behaviors of larger predators across the entire water column. Alongside them lived large bony fish, ancestral sea turtles of substantial size, and early representatives of marine reptile lineages that had been refining their aquatic adaptations for tens of millions of years. It is within this context that the first genuinely large marine predators of the Cretaceous must be understood. They did not appear suddenly or in isolation. Their scale and capability were the product of sustained evolutionary pressure within an environment that consistently rewarded size, speed, and sensory refinement. Resources were abundant, competition was persistent, and the physical dimensions of the seaway, warm, shallow, and enclosed on both sides by continental landmass, meant that organisms could not simply migrate away from predation pressure. They had to adapt to it, or be removed from the gene pool entirely. Before we dive deeper, drop a comment and let me know where you're watching from. I'm curious to see how far this reaches. Among the earliest large predators documented from this period are the plesiosaurs, a diverse group of marine reptiles that had originated in the Triassic and continued to diversify well into the late Cretaceous. Plesiosaurs are broadly divided into two functional body plans. The first, the plesiosauromorphs, were characterized by long, flexible necks, small heads, and relatively compact bodies. The second, the pliosauromorphs, developed shorter necks, larger skulls, and more powerful jaw musculature, a configuration optimized for capturing large, fast-moving prey. The pliosaurs, in particular, represent one of the more extreme examples of size scaling in Cretaceous marine fauna. Genera such as Kronosaurus, known from fossil material recovered in Australia and South America, are estimated to have reached lengths of approximately 9 to 10 meters, with skulls alone measuring over 2 meters in length. The dentition of these animals was robust and conical, designed for gripping rather than slicing, and biomechanical modeling of their jaw structure suggests bite forces comparable to those of the largest terrestrial predators of any geological period. Their limbs had been fully modified into hydrodynamic flippers, and locomotion was achieved through a form of underwater flight, and with the forelimbs generating the majority of propulsive force in a motion analogous to that of modern sea turtles, though substantially more powerful. What the fossil record makes clear is that animals of this scale were not ecological anomalies. They were the expected output of an environment in which prey biomass was exceptionally high, and competitive pressure favored the continued development of predatory capability. Evidence from bone chemistry and isotopic analysis suggests that the largest pliosaurs occupied the uppermost position in their food chains, feeding on other marine reptiles, large fish, and possibly on each other. There is isotopic and physical evidence of bite marks on pliosaur bones attributable to other pliosaurs, which indicates that intraspecific predation within the same species, was not uncommon. Alongside the plesiosaurs, the ichthyosaurs represented a second independent lineage of large marine reptiles. Although ichthyosaur diversity was declining by the mid-Cretaceous relative to their earlier Triassic and Jurassic peaks, several genera persisted into this period, retaining the streamlined, dolphin-convergent body form that made them among the fastest sustained swimmers in Mesozoic seas. Their large eyes, among the largest relative to body size of any vertebrate in the fossil record, suggest adaptation to low-light conditions, possibly indicating deep-diving behavior or crepuscular hunting patterns. Ophthalmosaurus, one of the better documented genera, possessed eyes with a diameter exceeding 20 centimeters and supported internally by a ring of sclerotic bones that maintained the eye's shape under the pressure changes associated with depth. The coexistence of multiple large predatory lineages within the same body of water raises immediate questions about resource partitioning. Current models suggest that ecological separation was maintained through a combination of depth preference, prey specialization, and geographic range within the seaway. Long-necked plesiosaurs are hypothesized to have operated primarily in mid-water and shallower zones, using their extended necks to ambush schooling fish and cephalopods. Pliosaurs, with their greater mass and more powerful locomotion, are thought to have ranged more widely through the water column and actively pursued larger prey. Ichthyosaurs, based on their body plan and eye morphology, may have specialized in faster, deeper, or more open water hunting strategies. This partitioning was not static. As the Cretaceous progressed and new predatory lineages emerged, most significantly the Mosasaurs, the competitive structure of the seaway shifted. Older groups declined or were displaced. The nature of that displacement and the characteristics of the animals that replaced them reveals something significant about how evolutionary pressure operated within this particular marine system. An environment this productive did not simply sustain large predators. It continuously produced new ones, each generation of apex fauna shaped by the accumulated selective force of an ecosystem that had been refining its own capacity for large-scale predation across geological timescales. The ocean recorded in Cretaceous sediments was not merely old or different from the present. It was, by measurable ecological criteria, operating at a level of biological intensity that has no direct modern equivalent. The size of the animals it supported, the density of predators across multiple trophic levels, and the competitive dynamics preserved in the fossil record collectively indicate a marine system under sustained and extreme biological pressure. Understanding what made that possible and what eventually brought it to an end requires examining each of the major groups that inhabited it, beginning with the lineage that ultimately came to dominate it more completely than any other. No other lineage defines the late Cretaceous marine environment as completely as the Mosasaurs. Their rise was geologically rapid, their ecological dominance was comprehensive, and their eventual disappearance was abrupt in a manner that continues to inform scientific understanding of extinction dynamics in marine systems. To examine the Mosasaurs is to examine what biological success looks like when an organism enters a productive environment at precisely the moment its competitors are in decline. Mosasaurs were not a single species. They were a diverse family of squamate reptiles, closely related to modern monitor lizards and, more distantly, to snakes, that transitioned from a semi-aquatic or coastal existence to full marine life sometime in the early late Cretaceous, approximately 98 million years ago. The transition itself is documented in the fossil record with reasonable clarity. Early mosasaur relatives, such as Dallosaurus from what is now Texas, were small, likely capable of movement on land, and showed only partial aquatic adaptation in their limb structure. Within a relatively short span of geological time, their descendants had elongated their bodies, transformed their limbs into paddle-like flippers, developed a tail fin supported by a downward bend in the vertebral column, and grown to sizes that placed them among the largest predators in any marine ecosystem of the Mesozoic. The speed of this transformation, measurable in tens of millions of years, which is rapid by evolutionary standards for body plan reorganization of this magnitude, reflects the degree of selective advantage available to a predator capable of fully exploiting the open water column of the Western Interior Seaway and equivalent late Cretaceous seas globally. The environment was, in a functional sense, waiting to be occupied at that level. When mosasaurs arrived, they filled it with a completeness that displaced or marginalized nearly every competing lineage. By the Campanian and Maastrichtian stages of the late Cretaceous, roughly 83 to 66 million years ago, mosasaur diversity had expanded substantially. Genera ranged from relatively small, agile forms of 2 to 3 meters in length to the largest known representatives, which current skeletal reconstructions place at between 13 and 17 meters. The variation in body form across the family was not random. It reflected genuine ecological differentiation, with different genera occupying distinct functional roles within the same broad marine environment. Platecarpus, a mid-sized genus recovered extensively from North American chalk deposits, possessed a body plan consistent with active pursuit predation in open water. Its tail morphology, revised significantly following more complete fossil discoveries in recent decades, is now understood to have included a well-developed fluke, a vertical tail fin analogous in function to that of modern sharks and cetaceans, though independently evolved. This feature would have provided substantial thrust for burst acceleration, a critical capability for an animal targeting fast-moving fish and cephalopods. Isotopic analysis of Platecarpus remains has been used to reconstruct its approximate position in the food chain and has suggested a diet consistent with mid-level marine prey rather than the largest available fauna. At the opposite end of the size spectrum, Tylosaurus and Mosasaurus itself represent the family's maximum known dimensions. Tylosaurus, recovered from the Niobrara Formation across Kansas and surrounding states, reached estimated lengths of 12 to 14 meters in the largest documented specimens. Its skull was elongated, with a distinctive rounded rostrum, the front of the snout, that lacked functional teeth at its tip, a feature that has led researchers to hypothesize ramming behavior as a predatory or competitive strategy, though this interpretation remains debated. The dentition further back in the jaw was robust and conical, suited to gripping prey rather than cutting it into smaller pieces, which implies that large prey items were consumed in large portions or whole. The stomach contents and associated fossil assemblages recovered alongside mosasaur remains provide direct evidence of diet in a way that skeletal morphology alone cannot. Several exceptionally preserved specimens contain identifiable material in the abdominal region, including fish scales, fragmentary ammonite shell, and in at least one documented case, the remains of a smaller mosasaur. This last point is significant. It confirms that cannibalism, or interspecific predation between mosasaur genera, was occurring within the same ecosystem, which has implications for understanding the competitive dynamics and population regulation of the group as a whole. Mosasaurus, the type genus from which the family takes its name, is known primarily from European material, particularly from the chalk deposits of the Maastricht region in the Netherlands, the source of the original specimens described in the late 18th century. Its estimated length in the largest reconstructions reaches approximately 17 meters, though as with all size estimates derived from incomplete skeletal material, this figure carries a margin of uncertainty. What is consistent across specimens is the robustness of the jaw structure and the nature of the tooth implantation. And mosasaur teeth were pleurodont, attached to the side of the jawbone rather than set in deep sockets, which made them more easily replaced through the animal's continuous tooth replacement cycle, but potentially more vulnerable to lateral stress during struggles with large prey. The presence of a second functional row of teeth on the palate, known as pterygoid teeth, provided additional gripping surface and reduced the probability of prey escape once contact had been made. The sensory biology of mosasaurs is an area of ongoing research. Evidence from the structure of the nasal passages and the configuration of the skull suggests that chemoreception, the detection of chemical signals in the water, was well developed, consistent with the conditions seen in their closest living relatives, the varanid lizards and snakes. This would have allowed mosasaurs to track prey or detect carcasses across considerable distances, supplementing visual detection in conditions of reduced water clarity. Inner ear morphology in some genera suggests reasonable low-frequency hearing capability, which may have aided in detecting pressure waves generated by the movement of large prey items through the water column. Geographically, mosasaurs were among the most widely distributed marine vertebrates of the late Cretaceous. Their remains have been recovered from every continent, including Antarctica, and from marine deposits spanning tropical, subtropical, and temperate paleoclimatic zones. This distribution reflects both the global connectivity of late Cretaceous seas, which were more extensively interconnected than present-day ocean basins due to elevated sea levels, and the ecological flexibility of the group itself. Different genera were adapted to different thermal and ecological conditions, and the family as a whole was capable of exploiting a broad range of marine environments. The relationship between mosasaur proliferation and the decline of other large marine reptile groups is documented clearly in the stratigraphic record. Ichthyosaur diversity had already been declining through the mid-Cretaceous for reasons not entirely resolved, with the last confirmed ichthyosaur specimens predating the peak of mosasaur dominance by several million years. Plesiosaur diversity similarly contracted through the Turonian and Coniacian stages, with the group largely disappearing from the record before mosasaurs reached their greatest ecological breadth. Long-necked plesiosaurs persisted alongside mosasaurs into the very end of the Cretaceous, and their coexistence suggests that niche partitioning remained viable, likely due to the plesiosaur's distinct body plan and probable dietary specialization relative to the larger mosasaur genera. Whether mosasaur expansion actively caused the decline of these groups through direct competition or predation pressure, or whether mosasaurs simply occupied ecological space that was becoming available due to independent decline processes, is a question the fossil record does not resolve with complete clarity. What the record does support is a directional pattern. Over the course of the late Cretaceous, mosasaurs increased in diversity, body size, and geographic range, while the other large marine reptile lineages contracted. The outcome, regardless of mechanism, was an ecosystem increasingly structured around mosasaurian dominance at the apex. By the final stages of the Cretaceous, the Maastrichtian Age, ending approximately 66 million years ago, mosasaurs occupied the top of the marine food chain across most of the world's oceans, with a comprehensiveness that few lineages in the vertebrate fossil record have matched. Their success was not the product of a single advantageous trait, but of a combination of features: body size, sensory capability, dietary flexibility, reproductive strategy, and thermal tolerance that together allowed them to function effectively across a wide range of environmental conditions and prey availability scenarios. That comprehensiveness made what followed all the more ecologically significant. An apex predator so thoroughly integrated into a global marine system does not disappear without leaving a measurable restructuring of the ecosystem it inhabited. The end Cretaceous extinction event, driven primarily by the consequences of the Chicxulub impactor, removed mosasaurs entirely and within a geologically brief interval. No lineage survived. No descendant group carried their ecological role forward into the Paleocene. The apex of the late Cretaceous ocean was vacated simultaneously with the apex of the terrestrial ecosystem, and the marine world that followed was, for millions of years, organized around the absence of the scale and predatory complexity that mosasaurs had represented. Understanding that absence and the nature of the system they left behind requires first understanding the full range of organisms that shared their ocean. Mosasaurs were the dominant force, but they were not the only large predator operating in those waters. In the rivers, estuaries, and coastal shallows bordering the late Cretaceous seas, a different kind of apex predator had been developing along its own independent trajectory, one that was, in terms of raw physical scale, among the largest crocodilian forms the planet has ever produced. The boundary between land and sea in the late Cretaceous was not a fixed or stable line. Coastlines shifted with fluctuating sea levels, river deltas extended and retracted across geological timescales, and the transitional zones between freshwater, brackish, and fully marine environments were wide, ecologically complex, and populated by organisms capable of functioning across multiple habitat types. It was within these transitional zones, the estuaries, floodplains, and coastal river systems of the late Cretaceous, that some of the largest crocodilian forms in the history of the planet developed and persisted. Crocodilians as a group have a deep evolutionary history. Their lineage extends back to the Triassic period, and the earliest members of the broader crocodiliform clade were terrestrial animals bearing little morphological resemblance to the semi-aquatic forms familiar today. Over the course of the Mesozoic, different branches of the crocodiliform tree explored a remarkable range of ecological strategies. Some became fully terrestrial cursorial predators, others developed herbivorous dentition, and several lineages independently evolved toward large-bodied, aquatic ambush predation. It is from this last trajectory that the giants of the Cretaceous coastal systems emerged. Among the largest crocodilians documented in the fossil record is Sarcosuchus imperator, recovered primarily from early Cretaceous deposits in the Sahara region of present-day Niger and Tunisia, formations that, during the time of deposition, represented a system of large river deltas and floodplains bordering the southern margin of the Tethys Sea. Sarcosuchus is estimated, based on skull-length scaling relationships derived from modern crocodilian proportions, to have reached a total body length of approximately 9 to 11 meters and a body mass in the range of 8,000 kilograms. These figures position it among the largest crocodilians known from any period of Earth history, though it is important to note that such estimates carry inherent uncertainty when derived from incomplete skeletal material and extrapolated using modern analogues that may not perfectly reflect the proportional relationships of extinct taxa. The skull of Sarcosuchus was exceptionally long and relatively narrow, a morphology broadly consistent with piscivorous specialization in modern long-snouted crocodilians, such as the gharial. However, the robustness of the jaw structure and the configuration of the posterior teeth suggest a more generalist predatory capability than strict fish-eating, and it is hypothesized that large individuals were capable of taking prey considerably larger than fish, including the dinosaurs and other large vertebrates that shared its riparian environment. A distinctive feature of the Sarcosuchus skull is the bulla, an enlarged bulbous expansion at the tip of the rostrum, the function of which has not been definitively established. Proposed explanations include enhanced olfactory capability, a role in sound production or resonance, or a secondary sexual characteristic associated with mate selection, though none of these hypotheses has been conclusively supported by available evidence. The osteoderms, the bony plates embedded in the skin along the dorsal surface of Sarcosuchus, were notably thick relative to body size, and growth ring analysis of these structures has been used to estimate both the longevity and the growth trajectory of the animal. Results from this analysis suggest that Sarcosuchus grew continuously throughout a lifespan estimated at 50 to 60 years, reaching its maximum known dimensions only in advanced age. This pattern of indeterminate growth, continued throughout life at a declining rate, is consistent with the condition observed in modern crocodilians and provides a mechanistic explanation for how individual animals within a long-lived lineage could attain body sizes substantially exceeding the average for their species. Equally significant, and in some reconstructions rivaling or exceeding Sarcosuchus in total length, is Deinosuchus, a crocodilian from the late Cretaceous of North America, whose fossil material has been recovered from multiple formations across the eastern and southwestern regions of the continent. Deinosuchus is of particular ecological relevance because its temporal range overlaps directly with the peak diversity of Mosasaurs in the adjacent western interior seaway, and its geographic distribution places it precisely in the coastal and estuarine zones that form the transitional boundary between that seaway and the continental interior. Size estimates for Deinosuchus have varied considerably across different analyses and specimen assessments, ranging from approximately 8 meters in more conservative reconstructions to upward of 12 meters in interpretations of the largest known material. A 2020 reassessment of Deinosuchus, incorporating previously undescribed specimens and revised taxonomic analysis, identified at least 3 distinct species within the genus and provided updated size estimates suggesting that the largest individuals approached or exceeded 10 meters in total length. Body mass estimates for animals of this size, derived from volumetric modeling, suggest weights in the range of 8,500 to perhaps as much as 8,000 kilograms, though these figures are inherently approximate. What distinguishes Deinosuchus ecologically from Sarcosuchus is not simply its temporal and geographic context, but the nature of the direct fossil evidence for its predatory behavior. Deinosuchus material has been recovered in association with, and in some cases directly articulated with, remains of large dinosaurs bearing bite marks attributable to its dentition. Bone from hadrosaur and ceratopsid specimens recovered from the same formations shows circular puncture marks and surface crushing, consistent with the tooth dimensions and jaw force expected for an animal of Deinosuchus's size. And this evidence supports the hypothesis that Deinosuchus was capable of ambushing and killing large terrestrial prey at the water's edge, a feeding strategy directly analogous to that employed by modern Nile and saltwater crocodiles, scaled upward to a degree that placed large herbivorous dinosaurs within its predatory range. The jaw mechanics of Deinosuchus are consistent with this interpretation. Unlike the elongated, narrow snout of a piscivore, Deinosuchus possessed a broad, robust skull with substantial depth through the posterior jaw region, a configuration that biomechanical modeling associates with high bite force generation and resistance to the torsional stresses produced when a large, struggling prey item is restrained. Estimates of bite force for large Deinosuchus individuals, derived from scaling relationships and jaw geometry, suggest values that would have been capable of crushing bone and penetrating the dermal armor present on many large dinosaur species. The ecological position of Deinosuchus within the late Cretaceous coastal system of North America represents a significant example of niche bridging, the occupation of predatory roles that span more than one habitat type. As a semi-aquatic ambush predator of substantial size, Deinosuchus would have functioned simultaneously as a major predatory force in freshwater and brackish river systems, and as an intermittent presence in the nearshore marine environment. Saltwater tolerance in large crocodilians is well documented in modern taxa. The saltwater crocodile of the Indo-Pacific region regularly enters marine environments and has colonized island habitats separated from continental land masses by open ocean crossings. And there is no compelling reason to exclude this capability from large Cretaceous crocodilians operating in a period of warm, shallow seas with extensive coastline connectivity. This bridging capacity has implications for the broader structure of the late Cretaceous predatory ecosystem. The coastal and estuarine zones occupied by Deinosuchus were not isolated from the marine environment of the western interior seaway. They were continuous with it, and the movement of prey, fish, marine reptiles entering shallow water, and terrestrial vertebrates approaching rivers and coastal zones would have created overlapping predatory territories between large crocodilians and the mosasaurs patrolling the adjacent seaway margins. Whether direct competitive interactions occurred between these two apex predator groups is not documented in the fossil record with certainty, but the geographic and ecological overlap makes some degree of interaction probable. It is also worth situating Deinosuchus within the broader diversity of large Cretaceous crocodilians, as it was not the only significant member of this group operating in the region. Apalachiosaurus and various less completely known crocodiliform taxa shared portions of the same continental and coastal environments, indicating that large crocodilian predators were a consistent and ecologically important component of these transitional zones throughout the late Cretaceous of North America. The diversity within the group suggests sustained ecological viability and resource availability sufficient to support multiple large-bodied predatory taxa in overlapping geographic ranges. The persistence of large crocodilians across the end Cretaceous extinction event, the same event that eliminated mosasaurs, non-avian dinosaurs, and pterosaurs entirely, is one of the more consequential selective outcomes of that interval. Deinosuchus itself did not survive. The genus disappears from the record several million years before the terminal Cretaceous boundary, likely during a period of regional environmental change that altered the coastal habitat structure it depended upon. But the broader crocodilian lineage persisted, and several groups crossed the extinction boundary into the Paleocene, where they continued to occupy semi-aquatic predatory roles in a world otherwise depleted of large vertebrate predators. The survival of crocodilians, while so many other large reptilian lineages perished, is hypothesized to relate to a combination of factors: their ability to tolerate extended periods of metabolic inactivity, their capacity to survive on infrequent large meals rather than requiring sustained prey availability, their semi-aquatic lifestyle, which may have provided some buffering from the atmospheric and thermal disruptions of the extinction event, and possibly their use of burrows or other sheltered microhabitats during the most acute phase of the crisis. These are characteristics that the Mosasaurs, as fully marine open water predators entirely dependent on sustained ocean productivity, did not share. The contrast between the fate of Deinosuchus and its relatives on one hand and the Mosasaurs on the other illustrates something fundamental about survival during mass extinction events. Ecological specialization toward maximum efficiency in a stable, productive environment provides significant advantages under normal conditions. But it may reduce resilience precisely when that environment undergoes rapid and severe disruption. The ocean that had sustained Mosasaurs for over 30 million years was itself changing, and the changes that would eventually destabilize it had been developing long before the asteroid impact brought the Cretaceous to its close. Before those changes are examined in detail, however, a complete account of the late Cretaceous marine ecosystem requires attention to the organisms that occupied its less immediately obvious ecological roles. The species whose body plans departed so substantially from familiar forms that they read, even in careful scientific reconstruction, as deeply improbable constructions of biological engineering. The late Cretaceous ocean was not populated exclusively by large streamlined predators operating within recognizable ecological frameworks. Alongside the Mosasaurs and Plesiosaurs, and distributed across every depth zone and habitat type within the global marine system, lived organisms whose body plans deviated from familiar animal architecture to a degree that makes their reconstruction from fossil material a genuinely challenging exercise. These were not marginal or rare forms. Many were abundant, ecologically significant, and in some cases globally distributed. Their strangeness, from a modern perspective, reflects not biological accident, but the degree to which evolution, given sufficient time and ecological space, will produce functional solutions that bear little surface resemblance to the forms we consider standard. Among the more structurally distinctive organisms of the late Cretaceous ocean were the ammonites, shelled cephalopods that had persisted and diversified across hundreds of millions of years of marine history, surviving multiple mass extinction events before finally disappearing at the end of the Cretaceous. The basic ammonite body plan, a soft-bodied animal occupying the outermost chamber of a coiled, gas-filled shell used for buoyancy regulation, is reasonably well understood. What is less immediately intuitive is the range of shell geometries that different ammonite lineages developed, particularly in the late Cretaceous, when a subgroup known as the heteromorph ammonites reached their greatest diversity. Heteromorph ammonites abandoned the tightly coiled planispiral geometry that characterizes the most familiar ammonite forms and instead developed shells that uncoiled into open spirals, straight shafts, hook shapes, or complex three-dimensional helical structures that appear, at first examination, to lack any clear adaptive logic. Nipponites, recovered from late Cretaceous deposits in Japan and North America, is among the most visually striking examples. Its shell formed an irregular, loosely organized tangle of connected whorls that does not conform to any simple geometric description. For some time after its initial description, researchers debated whether such a form could represent a functional, living animal, or whether it was a pathological variant. Subsequent analysis confirmed that Nipponites was a viable, apparently successful organism. Its shell geometry, while complex, maintained the structural integrity required for buoyancy regulation, and its geographic distribution suggests it was neither rare nor restricted to unusual environmental conditions. The adaptive significance of heteromorph shell geometries remains an area of active discussion. One hypothesis holds that uncoiling reduced the metabolic cost of shell construction by eliminating the geometric constraints of tight coiling. Another suggests that different shell orientations positioned the animal's feeding apparatus, the tentacles and beak of the soft body, in configurations better suited to particular prey capture strategies or depth zones. A vertically oriented straight-shelled ammonite, for example, would have hung in the water column with its tentacles directed downward, a posture potentially suited to capturing slow-moving or sessile prey from below. A hook-shaped shell might have positioned the animal near the seafloor or at the surface, depending on the orientation of its buoyancy chambers. These are hypotheses rather than confirmed conclusions, but they are consistent with the ecological diversity suggested by the range of heteromorph forms. The scale variation within ammonites also warrants attention. While many species fell within a size range of a few centimeters to perhaps 30 or 40 centimeters in shell diameter, the largest known ammonite, Parapuzosia sepenredensis, from the late Cretaceous of Europe, reached a shell diameter of approximately 2.5 meters in the largest documented specimen. An animal of this size, even accounting for the fact that the soft body occupied only a fraction of the total shell volume, represented a substantial presence in the water column and likely required significant food intake to sustain growth to that scale. The sheer size of the largest ammonites suggests that they were not simply passive filter feeders, but active participants in mid-water ecological dynamics, though the precise details of their feeding biology remain incompletely resolved. A separate category of biological improbability in the late Cretaceous ocean is represented by the rudists, a group of bivalve mollusks that constructed reef structures across tropical and subtropical shallow marine environments and developed body plans so divergent from the standard bivalve configuration that their classification as mollusks was a matter of historical debate. Rudists are bivalves, animals with two shells, but their two valves became dramatically asymmetrical over evolutionary time. The lower valve elongated into a cone, cylinder, or horn shape and anchored the animal to the substrate, while the upper valve reduced to a flat or slightly curved lid. In colonial aggregations, rudist individuals grew in dense clusters, with their elongated lower valves pressed together in formations that functioned ecologically as reefs, providing structural complexity and habitat for associated fauna in a manner broadly analogous to modern coral reefs, though through an entirely different biological mechanism. Rudist reefs were not a marginal feature of late Cretaceous shallow marine environments. For a substantial portion of the Cretaceous, they were the dominant reef-building structures in tropical seas, and displacing scleractinian corals from this ecological role across much of the low-latitude shallow marine zone. Their distribution extended across the Tethys Sea and into the carbonate platform environments of what is now southern Europe, North Africa, and the Middle East. Individual rudist shells could reach lengths of over a meter in the largest species, and the density of colonial aggregations produced limestone formations of considerable thickness that are preserved in the rock record across multiple continents. The mechanism by which rudists constructed these reefs and sustained growth rates sufficient to maintain reef structure against the constant erosive and biological forces acting on shallow marine carbonate environments is thought to have involved photosymbiotic relationships with algae, analogous to the zooxanthellae symbiosis in modern corals. Evidence for this hypothesis comes from shell microstructure and carbon isotope signatures consistent with photosymbiotic metabolism, though direct confirmation is not achievable from fossil material alone. If photosymbiosis was indeed present, it would explain the restriction of rudist reefs to shallow, well-lit tropical waters and their sensitivity to the environmental disruptions that accompanied the end Cretaceous extinction, disruptions that reduced light penetration and disrupted photosynthetic productivity across marine environments globally. In the open water column, away from reef structures and the sea floor, the late Cretaceous ocean supported populations of organisms that combined mobility with body plans of considerable structural novelty. Among these were the Eurypterids. No, by the late Cretaceous these had already declined. But more relevant are the various large predatory invertebrates that occupied mid-water and benthic niches. Tusoteuthis, a giant cephalopod recovered from the Niobrara Formation of North America, is estimated from fragmentary gladius material, the internal shell remnant, to have reached lengths of approximately 3.5 meters, with some estimates suggesting larger individuals were possible. As a soft-bodied animal, its preservation in the fossil record is inherently incomplete, but the scale of the recovered material indicates a predator of substantial size operating in the same water column as mosasaurs and large fish. The relationship between Tusoteuthis and the mosasaurs of the Western Interior Seaway is documented in at least one remarkable specimen, a mosasaur fossil bearing what has been interpreted as evidence of prey interaction with a large cephalopod, and separately, cephalopod gladius material recovered in association with mosasaur stomach contents. Whether large cephalopods functioned primarily as prey for mosasaurs, or whether sufficiently large individuals represented a genuine threat to smaller mosasaurs, is not definitively resolvable from available evidence, but the size estimates for Tusoteuthis place it within a range where interactions between the two groups would have been ecologically significant in either direction. The fish fauna of the late Cretaceous ocean contained its own representatives of structural improbability. A Xiphactinus, a large predatory bony fish reaching lengths of 4 to 6 meters, is known from exceptionally preserved specimens in the Niobrara Formation, including multiple examples preserving identifiable prey items within the body cavity. One particularly well-documented specimen contains the nearly complete skeleton of a smaller fish, Gillicus, of approximately 1.8 meters in length, swallowed whole and preserved in articulation within the ribcage of its predator. The preservation of this specimen, in detail sufficient to reconstruct the final meal of an individual animal that lived approximately 85 million years ago, illustrates both the quality of Cretaceous fossil preservation in certain formations and the scale of predatory interactions occurring routinely within this ecosystem. Xiphactinus itself, despite its size, was not an apex predator. It occupied a position within the food chain that made it prey for the larger mosasaurs and potentially for large sharks operating in the same waters. Its abundance in the fossil record suggests high population density, which in turn implies that the prey base sustaining it, smaller fish, cephalopods, and invertebrates, was itself extremely productive. The ecological pyramid of the Western Interior Seaway was not narrow at its base. It was broad, densely populated at every level, and supported a biomass sufficient to sustain multiple tiers of large predators simultaneously. The collective strangeness of these organisms, the uncoiling ammonites, the reef-building bivalves, the giant cephalopods, or the large predatory fish that were themselves prey, reflects the fundamental characteristic of the late Cretaceous marine environment. It was an ecosystem operating under conditions of high productivity, thermal stability, and evolutionary maturity that had been accumulating biological complexity for tens of millions of years. The body plans it produced were not strange in the context of that system. They were optimal solutions to the specific ecological problems posed by that specific environment. Their apparent improbability is a function of distance, the distance between the conditions that generated them and the conditions of the present ocean, which is cooler, lower in sea level, and organized around a fundamentally different set of ecological constraints. What that distance also obscures is the degree to which the late Cretaceous ocean was not merely diverse, but actively violent, structured at every level around predation, competition, and the continuous cycling of biomass through a food web of exceptional density and complexity. The strange forms described here were not passive inhabitants of a stable system. They were participants in an ecosystem where the pressure of predation was constant, where size and capability determined survival across every ecological niche, and where the sharks, already ancient by the Cretaceous, were undergoing their own trajectory of escalation that would produce forms as capable and as structurally refined as any predator in the history of the ocean. Sharks predate the late Cretaceous ocean by a margin so substantial that their presence within it represents not an origin, but a continuation. The latest expression of a lineage that had already persisted through several mass extinction events, survived the reorganization of global ocean chemistry on multiple occasions, and refined its basic biological architecture across more than 450 million years of continuous marine history. By the time mosasaurs were reaching their maximum diversity in the Campanian and Maastrichtian stages, sharks had already been present in marine ecosystems for longer than the current interval between the late Cretaceous and the present day. Their evolutionary trajectory through the Cretaceous was not one of emergence, but of escalation, an intensification of existing capabilities driven by the same competitive pressures that were simultaneously producing larger mosasaurs, more diverse plesiosaurs, and a denser, more productive prey base than the ocean had supported in preceding periods. The shark fauna of the early and mid-Cretaceous was already diverse, but it was during the late Cretaceous that several lineages underwent the size increases and morphological refinements that position them as significant ecological forces within a predator community already structured around very large animals. Understanding this escalation requires first establishing what sharks, as a biological group, were working with, the core features that had made them successful across hundreds of millions of years and that continued to provide the foundation for their Cretaceous development. The elasmobranch body plan, the shared architecture of sharks, rays, and their relatives, is built around a cartilaginous skeleton, a continuously replaced dentition, a highly refined electroreceptive sensory system, and a metabolic flexibility that allows different species to occupy thermal environments ranging from near-freezing deep water to warm tropical shallows. The replacement dentition is particularly significant from an evolutionary standpoint. Shark teeth are shed and replaced throughout the animal's life, with new teeth continuously forming in rows behind the functional front teeth and moving forward as anterior teeth are lost. An individual shark may produce tens of thousands of teeth across its lifespan. This biological feature has two important consequences. It means that sharks are represented in the fossil record primarily by their teeth, since cartilaginous skeletons rarely preserve. And it means that dental wear and breakage do not accumulate over time in the way they do in animals with fixed dentitions, allowing individual sharks to maintain full predatory capability throughout their lives. The electroreceptive system, concentrated in sensory organs known as the ampullae of Lorenzini, distributed across the snout and head, allows sharks to detect the weak electrical fields generated by the muscular activity of other animals. This capability functions at short range and is most effective in the final stages of a predatory approach, providing targeting precision independent of visual or acoustic information. Combined with the lateral line system, which detects pressure changes and water movement across considerable distances, sharks possess a sensory suite that allows effective predation in conditions of low visibility and at distances where other sensory modalities are insufficient. These capabilities were not new in the Cretaceous. They had been present in some form throughout the group's evolutionary history. What the Cretaceous environment provided was a prey base large and dense enough to reward their application at scales previously unavailable. Among the most ecologically significant shark lineages of the late Cretaceous was the family Cretoxorinidae, represented most prominently by Cretoxorina mantelli, a species recovered extensively from the Niobrara Formation and equivalent deposits across the western interior seaway region. Cretoxorina is estimated from tooth and vertebral centrum material to have reached lengths of approximately 6 to 7 meters, with robust, smooth-edged teeth consistent with a predatory strategy focused on large, fast-moving prey. Its vertebral centra, the calcified portions of the vertebral column that do preserve in the fossil record for some shark species, indicate a heavily built animal with the spinal reinforcement associated with powerful swimming and the physical stresses of subduing large prey. The fossil evidence for Cretoxorina's diet is unusually direct. Multiple specimens of large marine vertebrates from the Niobrara Formation bear tooth marks attributable to Cretoxorina, and in several cases, shed Cretoxorina teeth have been recovered in direct association with the remains of mosasaurs, plesiosaurs, and large fish. One documented specimen preserves a Cretoxorina tooth embedded in the vertebra of a Tylosaurus, a mosasaur genus that itself reached lengths of 12 meters or more. The implication is that Cretoxorina was capable of, and apparently engaged in, predatory or scavenging interactions with some of the largest marine reptiles of its environment. Whether such interactions represented active predation on living mosasaurs or feeding on carcasses is not resolvable from the fossil evidence alone. But the physical capability suggested by the size and dentition of Cretoxorina is consistent with either scenario. The teeth of Cretoxorina are morphologically convergent with those of the modern great white shark, large, triangular, with smooth cutting edges, rather than the serrated margins seen in some other large shark species. This convergence in tooth morphology is generally interpreted as reflecting convergence in predatory strategy, a focus on large, high-energy prey items taken with powerful biting rather than sustained pursuit or filter feeding. The smooth edge, counterintuitively, may be more effective than serration for penetrating the thick, cartilaginous or bony integument of large vertebrate prey, as it concentrates cutting force along a continuous edge rather than distributing it across serration points. This interpretation, if correct, suggests that Cretoxorina had evolved a predatory toolkit specifically calibrated to the large prey available in its environment. Alongside Cretoxorina, the late Cretaceous ocean supported a diversity of other shark forms occupying different ecological positions. Squalicerax, known from abundant tooth material across multiple continents, was a medium-sized shark, estimated at 3 to 5 meters, with strongly serrated teeth more suited to cutting through flesh and bone than the smooth-edged teeth of Crocodilian. Squalicerax teeth have been recovered in association with a remarkable range of prey material, including marine reptiles, large fish, and terrestrial dinosaurs. The last category indicating that Squalicerax, like large modern sharks, and was an opportunistic scavenger willing to feed on carcasses that entered the marine environment from terrestrial sources. The serrated dentition of Squalicerax is functionally analogous to that of modern tiger sharks, which are similarly generalist and opportunistic in their feeding behavior, and this morphological parallel suggests a broadly comparable ecological role. The presence of both Crocodilian and Squalicerax in the same depositional environments indicates that the late Cretaceous shark fauna was not ecologically redundant. Different species occupied different functional positions within the predator community, reducing direct competition through dietary and behavioral differentiation. This partitioning is consistent with the broader pattern of ecological complexity in the Western Interior Seaway and equivalent environments, a system dense enough in resources to support multiple large predatory species at each trophic level without competitive exclusion driving diversity reduction. Deeper in the water column and in open oceanic environments beyond the shallow seaway, additional shark lineages were developing along trajectories less well documented in the fossil record due to the reduced preservation potential of deep water deposits. The ancestors of several modern shark families were present during the late Cretaceous, and the diversification of these groups during this period laid the foundation for the shark fauna that would persist and continue to evolve following the end Cretaceous extinction. Unlike the Mosasaurs and large marine reptiles, multiple shark lineages crossed the extinction boundary and survived into the Paleocene, a resilience that reflects both their biological flexibility and the extent to which their basic body plan had been stress-tested across geological timescales, far exceeding those of any competing lineage. The trajectory of shark evolution through the Cretaceous also provides the earliest context for understanding the lineage that would eventually produce Otodus megalodon, the largest macropredatory shark in the fossil record, which did not appear until the Cenozoic, but whose ancestral line extends back through Otodus obliquus and related forms into the late Cretaceous. Otodus obliquus itself, present in late Cretaceous and early Paleogene deposits, was a large shark with teeth exceeding those of Crocodilian in size, representing a continuation of the size escalation trend that characterized the most productive intervals of Cretaceous shark evolution. The existence of this lineage in the Cretaceous does not diminish the distinctiveness of megalodon as a Cenozoic phenomenon, but it situates that later development within a continuous evolutionary trajectory rather than treating it as an isolated occurrence. What the Cretaceous shark record collectively demonstrates is that the escalation of predatory capability in this group was not a response to any single environmental trigger, but a sustained process driven by consistent selective pressure in environments where large prey was reliably available and where the competition for that prey was intense. Sharks were not the largest predators in the late Cretaceous ocean. The largest mosasaurs exceeded the largest known Cretaceous sharks in total length, but they occupied predatory roles that the marine reptiles could not fully replicate, and their sensory capabilities, metabolic flexibility, and biological durability made them effective competitors across a range of conditions that other large predators could not match. The cumulative effect of having mosasaurs, plesiosaurs, large sharks, giant cephalopods, and numerous other large predatory forms operating simultaneously within the same marine system, was an ecosystem of predatory density and competitive intensity without clear parallel in the modern ocean. The violence implicit in such a system was not incidental or occasional. It was structural, built into the basic organization of the food web by the sheer number and scale of predators relative to the prey base sustaining them. What that meant for the day-to-day functioning of the ocean, and what the fossil record reveals about the actual nature of predatory interactions within it, forms the necessary next stage of this examination. The concept of violence applied to an ecosystem requires precise definition. In ecological terms, it does not refer to aggression in any behavioral or intentional sense, but to the rate and intensity of predatory interactions relative to the total biomass of the system, the frequency with which organisms at every trophic level were being killed, consumed, or injured within a given unit of time and space. By this measure, the late Cretaceous ocean presents a case that is difficult to parallel in either the modern marine environment or in other intervals of the fossil record. The density of large predators, the diversity of predatory strategies operating simultaneously, and the direct physical evidence of predatory interaction preserved across multiple formations collectively indicate a system in which lethal predatory contact was not an exceptional event, but a near constant feature of ecological functioning. The fossil record does not preserve behavior directly. What it preserves are the physical consequences of behavior: bite marks on bone, healed injuries in skeletal material, shed teeth in association with prey remains, and the spatial relationships between predator and prey in depositional contexts. From these physical traces, it is possible to reconstruct, with varying degrees of confidence, the nature and frequency of predatory interactions in extinct ecosystems. The late Cretaceous marine record is unusually rich in this type of evidence, partly because the chalk and limestone formations deposited in environments like the Western Interior Seaway preserve skeletal material with exceptional fidelity, and partly because the sheer density of predators in these environments means that evidence of predatory interaction is distributed widely through the fossil assemblages. Bite mark analysis on late Cretaceous marine vertebrate remains has been conducted across multiple taxa and formations, and the results consistently indicate high rates of predatory contact. Plesiosaur bones from the Niobrara Formation show bite marks attributable to mosasaurs, sharks, and in some cases to other plesiosaurs. Mosasaur bones show bite marks attributable to larger mosasaurs and to Cretoxyrhina, where fish remains show bite marks from multiple predator types simultaneously. A single large Xiphactinus specimen may show evidence of shark predation on its fins, mosasaur bite marks on its flanks, and internal evidence of its own predatory activity through preserved stomach contents. The layering of this evidence within individual specimens reflects an ecosystem in which predatory pressure was applied from multiple directions simultaneously, and in which no organism above a minimal size threshold was exempt from predatory attention. The healed injury record is equally informative. Healed bite marks, injuries that show bone remodeling indicating survival of the initial predatory contact, are documented in mosasaur, plesiosaur, and large fish material from late Cretaceous deposits. The existence of healed injuries demonstrates that predatory attacks did not always result in immediate death and consumption, and that animals capable of surviving initial contact continued to live and accumulate further evidence of predatory interaction over time. Several mosasaur specimens show multiple healed injuries on different skeletal elements, suggesting repeated predatory contact across the lifetime of a single individual. This pattern is consistent with an environment in which predatory encounters were frequent enough that even large, capable animals experience them repeatedly rather than occasionally. The implications of this injury frequency extend beyond simple documentation of predatory activity. High rates of predatory contact in a population have measurable effects on population structure, behavior, and evolutionary trajectory. Populations experiencing intense predation pressure show accelerated selection for anti-predator adaptations, increased body size, thicker integument, more effective escape locomotion, or behavioral modifications that reduce exposure to predation risk. In the late Cretaceous marine system, the evidence suggests that these selective pressures were operating across multiple lineages simultaneously, producing a kind of evolutionary arms race in which predatory capability and anti-predator adaptation escalated in parallel across the entire community. The scale of individual predatory events documented in the fossil record provides additional context for understanding the intensity of this system. The consumption of prey items approaching or exceeding the body size of the predator, documented in Xiphactinus specimens containing large fish, in Mosasaur stomach contents including substantial marine vertebrates, and in the bite mark evidence indicating attacks on animals of comparable size, reflects a predatory ecology in which energy return per predatory event was maximized by targeting the largest available prey. This strategy, while energetically efficient when successful, also implies that predatory interactions were physically intense and potentially dangerous to the predator as well as the prey. An animal attempting to subdue prey of comparable body mass risks injury from the prey's defensive responses, and the healed injury record in late Cretaceous predators suggests that such injuries were common, and the competitive structure among predators in this system was not organized around simple dominance hierarchies. Multiple large predator types occupied overlapping size ranges and geographic zones, and the evidence suggests that competitive interactions between predator species, including direct predation of one predator type by another, were a regular feature of the ecosystem. The documentation of Mosasaur remains with shark bite marks, shark remains with Mosasaur bite marks, and Plesiosaur remains with injuries attributable to multiple predator types simultaneously indicates a predator community in which no single lineage held unchallenged dominance across all contexts and size classes. Even the largest mosasaurs, which occupied the apex position in terms of maximum body size, it was subject to predatory or competitive pressure from large sharks in contexts where size advantage was reduced, in turbid water, at night, or in the initial stages of an ambush, before the mosasaur's full locomotive capability could be brought to bear. The shallow depth profile of the Western Interior Seaway is relevant to understanding predatory intensity. A shallow epicontinental sea with maximum depths of several hundred meters and extensive zones of much shallower water across broad areas concentrates its biological productivity, and therefore its prey biomass, within a relatively compressed vertical range. In modern deep ocean basins, prey can distribute itself across thousands of meters of water column, reducing encounter rates with predators through simple spatial dilution. In a shallow sea, this vertical refuge is unavailable. Prey must remain within the same depth zone as its predators, and the concentration of both prey and predator within a limited vertical space increases encounter rates above what would be expected in a deeper system of equivalent surface area. The thermal homogeneity of the late Cretaceous seaway contributed to this concentration effect. Without strong thermoclines, the sharp temperature gradients that in modern oceans create distinct biological zones at different depths and often serve as partial barriers to predator movement, the water column of the Western Interior Seaway was more uniformly accessible to large predators across its full depth range. Predators that in a modern stratified ocean might be restricted to surface or deep water by thermal preferences could, in the isothermal or weakly stratified Cretaceous seaway, move freely through the entire water column, further increasing their encounter rates with prey distributed at any depth. The productivity of the system, the rate at which photosynthesis at the surface generated organic carbon that flowed through the food web, was itself a driver of predatory intensity rather than simply a consequence of it. High surface productivity generated large prey populations, which in turn supported large predator populations, which imposed intense predation pressure on prey, which selected for faster reproduction and higher population turnover rates in prey species, which maintained high prey biomass despite heavy predation. This feedback loop, operating across multiple trophic levels simultaneously, produced an ecosystem in a state of high energy cycling, large amounts of biomass being continuously produced and consumed at rates substantially higher than those characteristic of less productive marine systems. The geochemical record from late Cretaceous marine sediments supports this interpretation of high productivity. Carbon isotope ratios in carbonates deposited during this period reflect elevated rates of organic carbon burial, a signature consistent with high surface productivity, generating more organic material than the decomposer community could fully process before it sank and was incorporated into sediment. Phosphorus concentrations in some formations indicate upwelling of nutrient-rich deep water into the photic zone, a process that in modern oceans is associated with the most biologically productive marine environments, such as the coastal upwelling zones off Peru and Namibia. The combination of warm temperatures, high sea levels flooding nutrient-rich continental margins, and likely elevated atmospheric carbon dioxide concentrations, creating enhanced greenhouse conditions, produced a marine environment with a photosynthetic base substantially more productive than the modern global ocean average. This productivity was the foundation upon which the entire predatory structure of the late Cretaceous ocean rested. Without it, the biomass necessary to sustain multiple tiers of large predators simultaneously would not have been available. With it, the system could support a predator density and diversity that by any measurable ecological criterion exceeded what the modern ocean maintains. The violence of the late Cretaceous ocean was not a random or contingent feature. It was the direct and predictable outcome of a highly productive system operating under conditions that maximized biological density at every trophic level. Understanding the structure of that violence, how energy and biomass moved through the system, how predator populations were regulated, and what the internal dynamics of such a dense predator community looked like in functional terms, requires examining the food web not as a static hierarchy, but as a dynamic, continuously active process of energy transfer and competitive interaction. It is in this examination that the most consequential features of the late Cretaceous marine ecosystem become apparent, features that were not only the source of its biological intensity, but also, ultimately, the foundation of its vulnerability. A food chain, in the most reductive sense, is a description of who eats whom. In practice, the ecological structures that sustain complex marine communities are considerably more dynamic than this framing implies. They are better understood as food webs, networks of intersecting predator-prey relationships in which energy flows along multiple pathways simultaneously, in which the same organism may function as predator in one interaction and prey in another, and in which the stability of the entire system depends on the maintenance of functional relationships across all trophic levels at once. the late Cretaceous marine food web was among the most complex and densely interconnected of any documented in the fossil record, and its internal dynamics were characterized by a level of continuous predatory activity that makes the concept of a stable equilibrium difficult to apply with any precision. The base of this food web, as in all marine systems, was photosynthetic. Phytoplankton, microscopic single-celled algae and cyanobacteria floating in the sunlit surface layer of the ocean, converted solar energy and dissolved carbon dioxide into organic carbon through photosynthesis, producing the primary biomass upon which all subsequent trophic levels depended. In the late Cretaceous, the phytoplankton community was dominated by calcareous nanoplankton, organisms that produced minute calcium carbonate plates called coccoliths, and by dinoflagellates, diatoms, and other groups whose collective productivity, as reflected in the carbon isotope and sedimentary record, was high relative to modern baselines. The chalk formations that define much of the late Cretaceous stratigraphic record across Europe, North America, and other regions are themselves composed largely of accumulated coccolith material, the compressed remains of trillions of individual phytoplankton cells that sank to the seafloor over millions of years, a physical testament to the scale of primary production operating at the surface. Zooplankton, small animals and animal-like protists that fed on phytoplankton and on each other, formed the second trophic level, transferring energy from the photosynthetic base upward into the food web in forms accessible to larger organisms. Foraminifera, small crustaceans, larval invertebrates, and various other planktonic forms constituted this layer, and their abundance in the fossil record from late Cretaceous marine deposits indicates populations of high density distributed across the full surface area of the seaway. The transfer efficiency between trophic levels, the proportion of energy available at one level that is successfully incorporated into the biomass of the next, is never complete, with typical values in marine systems ranging from roughly 10 to 20%. This means that sustaining large predators at the apex of a food web requires an exceptionally productive base, and the scale of phytoplankton production in the late Cretaceous ocean was, by multiple independent geochemical measures, sufficient to support the predator densities the fossil record documents. The next trophic level above zooplankton was occupied by small to medium-sized fish, cephalopods, and filter-feeding invertebrates that consumed planktonic material directly or fed on organisms that did. This level was where the diversity and abundance of the late Cretaceous food web became most immediately visible in the fossil record. Fish fauna from the western interior seaway and equivalent formations include dozens of species spanning a wide range of body sizes and feeding strategies, from small, schooling forms analogous to modern herrings and anchovies that fed directly on zooplankton, to mid-sized predatory fish occupying intermediate positions in the food web. Ammonites, distributed across multiple size classes and depth zones, contributed to this middle trophic level through their consumption of zooplankton and small invertebrates, while themselves serving as prey for virtually every larger predator in the system. The density of prey at this intermediate level was what made the upper trophic levels possible. Large predators require large amounts of prey biomass to sustain themselves, and the energy cost of maintaining a body of several hundred or several thousand kilograms in an aquatic environment, even accounting for the buoyancy support that reduces locomotion costs relative to terrestrial movement, is substantial. A mosasaur of 10 meters in length, operating as an ectotherm with metabolic rates substantially lower than those of a comparable-sized mammal, would still have required regular and substantial food intake to sustain growth, reproduction, than basic physiological maintenance. The fossil evidence of large predator abundance in the western interior seaway implies a prey base capable of supporting those energy demands across the full predator population simultaneously. A prey base that was itself continuously replenished by the productivity flowing upward from the phytoplankton base. The flow of energy through this system was not unidirectional or simple. Omnivory, feeding at multiple trophic levels simultaneously, was common across the food web. Large mosasaurs consumed fish, cephalopods, marine reptiles, and invertebrates, drawing energy from multiple trophic positions rather than a single prey category. Sharks scavenged carcasses as well as actively hunting living prey, or recycling biomass that might otherwise be lost to bacterial decomposition before it could be accessed by larger consumers. Sea turtles, which were diverse and abundant in late Cretaceous marine environments, consumed both animal prey and marine vegetation, linking the photosynthetic base directly to mid-level consumers in pathways that bypass the standard zooplankton fish energy transfer route. This trophic complexity increased the resilience of individual predator populations to fluctuations in any single prey type. If one prey category declined temporarily, generalist predators could shift to alternatives. But it also meant that disturbances propagating through the food web were transmitted along multiple pathways simultaneously, rather than being contained within a single trophic chain. The regulation of predator populations in this system was achieved primarily through food limitation and intraspecific competition, rather than through predation on the predators themselves, though as the evidence for predator-on-predator interactions demonstrates, the latter was not absent. In modern marine ecosystems, apex predator populations are regulated through a combination of prey availability, reproductive rates, and territorial or social competition for resources. In the late Cretaceous system, the high prey availability documented by the fossil record suggests that food limitation was less constraining than in many modern environments, which would have allowed predator populations to reach densities higher than those typical of modern apex predators. The consequence of high predator density was, in turn, an intensified competition among predators for the available prey base, a feedback that maintained predatory pressure at high levels across the entire community. The concept of trophic cascades, the propagation of ecological effects downward through the food web from changes at the apex, is well documented in modern marine systems. The removal of apex predators from modern ecosystems through human exploitation consistently produces measurable reorganization of lower trophic levels. Prey populations increase, their food resources are depleted, and the structure of the community shifts in ways that can reduce overall productivity and stability. In the late Cretaceous system, the presence of apex predators at unusually high densities would be expected to produce the inverse effect: strong top-down suppression of prey populations and maintenance of high prey turnover rates, and a continuous downward pressure on intermediate trophic levels that kept the entire food web in a state of active, high-energy cycling. This state of continuous cycling had consequences for the physical environment of the seaway, as well as for its biological community. High rates of organic carbon production at the surface, combined with high consumption rates throughout the water column, meant that the proportion of surface-produced organic material reaching the seafloor as intact particles was variable and dependent on the balance between production and consumption at each depth. In periods when surface productivity was high and water column consumption was insufficient to process all the sinking organic material, organic carbon accumulated on the seafloor in quantities that could drive localized oxygen depletion through microbial decomposition. The sedimentary record of the Western Interior Seaway shows evidence of periodic bottom water anoxia, zones of oxygen depletion near the seafloor, particularly in the deeper central portions of the seaway where water circulation was limited. These anoxic intervals, recorded as dark, laminated, organic rich sediment layers, interbedded with the more typical chalk and limestone of the formation, indicate that the productivity of the surface system was, at times, exceeding the capacity of the water column to fully process its output. This is a significant observation because it suggests that the late Cretaceous food web, despite its complexity and the apparent efficiency of its predator community, and was operating at an intensity that periodically overwhelmed the decomposer system and produced localized zones of environmental stress within the otherwise productive seaway. The implications of this observation extend beyond the immediate depositional context. A food web operating at the edge of its processing capacity, producing organic material at rates that periodically exceed decomposition rates and generate bottom water oxygen depletion, is a system with reduced buffering capacity against external perturbations. If surface productivity were to increase further, or if water column circulation were to decrease, or if any other factor were to shift the balance between production and decomposition, the system could move from periodic localized anoxia toward more widespread and sustained oxygen depletion. The sedimentary record suggests that this transition from a highly productive but locally stressed system to one experiencing broader environmental deterioration was not a hypothetical future scenario for the late Cretaceous ocean. It was something that had already begun, and its progression would have consequences for every organism in the food web, from the phytoplankton at the base to the mosasaurs at the apex. The food chain built on constant killing was also, in this sense, a system constantly generating the conditions for its own eventual destabilization. The very processes that sustained its biological intensity, high productivity, high predator density, continuous biomass cycling, were simultaneously producing chemical and physical changes in the water column that would, over geological timescales, begin to undermine the stability of the environment those processes depended upon. The transition from this recognition to an examination of the environmental changes themselves marks the point at which the history of the late Cretaceous ocean shifts from a story of biological success to one of incremental and ultimately catastrophic deterioration. Environmental change in marine systems rarely announces itself through sudden discrete events visible at human timescales. It accumulates through incremental shifts in physical and chemical parameters, water temperature, salinity, circulation patterns, nutrient availability, oxygen concentration, that individually may fall within the normal range of seasonal or decadal variability, but that, sustained over centuries or millennia, reorganize the fundamental structure of the ecosystem. The late Cretaceous ocean began changing in ways that would ultimately prove catastrophic well before the end Cretaceous boundary event, and the evidence for this change is distributed across multiple lines of geological and geochemical data that, taken together, describe a system under increasing stress from several converging directions simultaneously. The first and most broadly documented of these changes involves sea level. Throughout the Cretaceous, global sea levels had remained elevated, substantially above modern baselines, due to the combination of high global temperatures, the absence of significant polar ice, and elevated rates of seafloor spreading that displaced ocean water upward onto continental margins. The Western Interior Seaway, along with numerous other epicontinental seas globally, existed precisely because sea levels were high enough to flood the low-lying interiors of continental landmasses. As the late Cretaceous progressed into the Campanian and Maastrichtian stages, sea levels began a general regression, a gradual but measurable decline that progressively reduced the extent and depth of shallow epicontinental marine environments worldwide. The causes of this regression were multiple and interacting. Declining rates of seafloor spreading reduced the displacement of ocean water onto continental margins. Gradual cooling of global temperatures relative to the thermal maximum of the mid-Cretaceous began to sequester water in polar and high-latitude ice accumulation, though large-scale glaciation did not develop until well into the Cenozoic. Tectonic uplift along the western margin of North America, driven by the ongoing Laramide orogeny, the mountain-building episode that produced the ancestral Rocky Mountains, progressively elevated the western shoreline of the Western Interior Seaway and reduced the seaway's basin depth and surface area from its western margin inward. The ecological consequences of sea level regression in a shallow epicontinental system are significant and directional. As water depth decreases and the surface area of the sea contracts, the total volume of habitat available to marine organisms diminishes. Organisms adapted to open water or mid-depth environments find their available range compressing toward the remaining deeper central portions of the shrinking sea. Benthic communities, those living on or near the seafloor, experience habitat loss directly as previously submerged seafloor is exposed by the regressing shoreline. The connectivity between the epicontinental sea and adjacent marine environments may be reduced or interrupted entirely as the sea shallows and narrows, limiting the exchange of water, nutrients, and organisms with the broader ocean. For the Western Interior Seaway specifically, the regression that characterized the late Campanian and Maastrichtian was not a single continuous event, but a series of transgressive and regressive pulses superimposed on a general long-term trend towards shallowing and contraction. Stratigraphic analysis of the formations deposited during this interval records alternating intervals of deeper and shallower water conditions, reflecting the complex interplay of tectonic, eustatic, and climatic factors controlling sea level at regional and global scales. The overall trajectory, however, was one of progressive reduction, a seaway that had, at its maximum extent, stretched continuously from the Arctic to the Gulf of Mexico, gradually fragmenting, shallowing, and ultimately disappearing as a continuous marine body by the end of the Cretaceous period. Concurrent with sea level regression, evidence from the paleoclimate record indicates a gradual cooling of global temperatures through the latest Cretaceous, relative to the thermal maximum of the Cenomanian-Turonian interval, approximately 90 to 94 million years ago. This cooling, documented through oxygen isotope ratios in carbonate microfossils and through changes in the geographic distribution of temperature-sensitive fauna and flora, was not of sufficient magnitude to constitute glaciation or to produce the dramatic thermal gradients of later Cenozoic climate states. But it was measurable, sustained, and ecologically consequential for organisms adapted to the consistently warm conditions that had characterized the Cretaceous peak. For marine reptiles in particular, mosasaurs, plesiosaurs, and the remaining large reptilian fauna of the late Cretaceous sea, thermal conditions were a fundamental constraint on physiology and distribution. Current evidence suggests that mosasaurs, like most large reptiles, were ectothermic, or at most had limited endothermic capability, meaning that their metabolic rates, activity levels, and reproductive success were directly influenced by ambient water temperature. Some isotopic studies of mosasaur tooth material have been interpreted as suggesting partial thermal regulation, the ability to maintain body temperatures somewhat above ambient water temperature through metabolic heat generation. But the degree and reliability of this capability across different mosasaur genera is not established with certainty. Even if some degree of thermal buffering was present, a sustained directional cooling of ocean temperatures would have progressively shifted the geographic ranges of thermally sensitive species toward lower latitudes and reduced the total area of habitat within optimal thermal parameters. Species unable to track their preferred thermal zone through geographic range shifts, because the geometry of the regressing and contracting seaway limited available migration routes, would have experienced increasing physiological stress and reproductive difficulty as temperatures declined below the range optimal for their metabolic function. The oceanographic consequences of cooling extend beyond direct thermal effects on individual organisms. Cooler water holds more dissolved oxygen than warm water, which in isolation would appear beneficial for aerobic marine life. However, cooler temperatures also affect the density stratification of the water column and the patterns of ocean circulation that drive the upwelling of nutrient-rich deep water into the photic zone. Changes in circulation patterns can reduce or redirect upwelling, decreasing the nutrient supply to surface waters and reducing primary productivity, the photosynthetic base upon which the entire food web depends. If cooling-induced circulation changes reduce the nutrient supply to the late Cretaceous surface ocean, the effect would propagate upward through the food web from the phytoplankton base, reducing prey availability at every subsequent trophic level and placing the large, energetically demanding predators at the apex under increasing resource stress. The record of primary productivity changes in the latest Cretaceous is complex and varies by region, but several studies using carbon isotope and organic carbon burial records suggest that productivity fluctuated significantly through the Maastrichtian, with some intervals showing evidence of reduced surface productivity relative to the Campanian peak. These fluctuations, even if temporary, would have had cascading effects through a food web as densely populated and energetically demanding as that of the late Cretaceous marine system. A reduction in prey availability in a system already operating at high predator density would have increased competitive pressure among predators rapidly, potentially driving population declines in the most energetically demanding species before any other environmental stressor became significant. Volcanic activity during the latest Cretaceous introduces another dimension of environmental perturbation that is increasingly recognized as having contributed to the deteriorating conditions of the period. The Deccan Traps, a large igneous province in what is now the Indian subcontinent, were erupting episodically throughout the late Maastrichtian, releasing substantial quantities of carbon dioxide, sulfur dioxide, and other volcanic gases into the atmosphere. The climatic effects of large igneous province volcanism are complex and depend on the relative timing and magnitude of different gas emissions. Carbon dioxide release tends to produce warming, while sulfur dioxide aerosols produce short-term cooling. The net effect of Deccan volcanism on latest Cretaceous climate is still debated, but evidence from paleoclimate proxies suggests that volcanic episodes were associated with measurable perturbations in ocean temperature and chemistry that added to the background stress already imposed by sea level regression and the longer-term cooling trend. Ocean acidification, the reduction of seawater pH resulting from the absorption of atmospheric carbon dioxide, is a chemical consequence of elevated volcanic outgassing that would have had direct effects on the carbonate-shelled organisms forming much of the base and middle of the late Cretaceous food web. Ammonites, with their calcium carbonate shells, and the calcareous nanoplankton constituting the primary photosynthetic base were both vulnerable to acidification-driven dissolution of their shell material and to the metabolic costs of maintaining calcification in waters of reduced carbonate saturation. Even modest acidification, sustained over ecologically relevant timescales, can reduce calcification rates, impair reproduction, and decrease population sizes in carbonate-dependent organisms, effects that would have propagated upward through the food web to every level dependent on those organisms as a food source. The confluence of these environmental changes, sea level regression, reducing available habitat, gradual cooling, altering thermal conditions and circulation patterns, volcanic perturbations, introducing episodic chemical and climatic stresses, and the cumulative effects of sustained high biological intensity, was producing an ocean under measurably increasing stress through the final millions of years of the Cretaceous. The system had not yet collapsed. The large predators documented in Maastrichtian deposits were still present, still diverse, and still ecologically active. But the conditions sustaining them were becoming less stable, and the margins within which the system could absorb further perturbation without reorganization were narrowing. The most chemically consequential expression of this narrowing, the process that most directly threatened the physiological viability of organisms across the water column, was not temperature change or sea level shift, but the alteration of the ocean's dissolved oxygen budget. A change whose physical and biological consequences were more immediately lethal than any of the gradual environmental shifts that preceded it, and whose development drew directly on the same high productivity that had defined the late Cretaceous marine system at its biological peak. Dissolved oxygen in the ocean is not a fixed or guaranteed resource. It is a dynamic parameter, continuously produced through photosynthesis in the sunlit surface layer and consumed through the respiration of every aerobic organism in the water column and on the seafloor. Its distribution at any given depth and location reflects the balance between these production and consumption processes, mediated by the physical transport of oxygen-rich surface water into the interior of the ocean through circulation and mixing. When this balance shifts, when consumption exceeds supply in a given water mass, or when physical circulation slows and reduces the delivery of oxygenated water to depth, dissolved oxygen concentrations decline, and the consequences for aerobic life are direct, measurable, and in sufficiently severe cases, lethal. The geological record contains evidence of numerous intervals during which this balance shifted dramatically, producing what are known as oceanic anoxic events, periods during which substantial portions of the global ocean became depleted of dissolved oxygen to a degree that caused widespread mortality among oxygen-dependent organisms and left a distinctive chemical and sedimentary signature in the rock record. The most severe of these events occurred during the Cretaceous, and while the major oceanic anoxic events of the early and mid-Cretaceous predate the biological peak discussed in preceding chapters, the processes that generated them did not disappear with the formal end of those events. They persisted in attenuated form throughout the late Cretaceous, and the sedimentary record of formations like the Western Interior Seaway shows clear evidence of repeated, localized oxygen depletion events distributed through the Campanian and Maastrichtian stages, a pattern indicating that the ocean's oxygen budget remained under stress even as the biological community above the seafloor reached its maximum complexity and predator density. The fundamental mechanism driving oxygen depletion in the late Cretaceous ocean was the same one that generates modern oxygen minimum zones, and that produced the major anoxic events of earlier Cretaceous intervals. The sinking of organic material from productive surface waters into a water column and onto a seafloor where its decomposition by aerobic bacteria consumed dissolved oxygen faster than physical circulation could replenish it. In a highly productive surface ocean, the quantity of organic material sinking from the photic zone through the death of phytoplankton, the sinking of zooplankton fecal pellets, and the descent of larger organic particles can be substantial. Much of this material is consumed in the upper water column before reaching depth, but in conditions of high productivity, a significant fraction reaches the deeper water and the seafloor, where its decomposition drives localized oxygen depletion. The rate at which oxygen-depleted deep water is replenished depends on the strength and pattern of ocean circulation. In the modern ocean, the thermohaline circulation, driven by the sinking of cold, dense, oxygen-rich water at high latitudes, continuously ventilates the deep ocean and transporting dissolved oxygen from the surface to depth and maintaining aerobic conditions across most of the seafloor. In the late Cretaceous ocean, with its substantially higher global temperatures, reduced latitudinal temperature gradients, and absence of cold polar water masses, the thermohaline circulation was weaker and less efficient than today. The density contrasts driving deep water formation were reduced. The sinking of dense surface water at high latitudes was less vigorous, and the ventilation of the deep ocean interior proceeded more slowly. This reduced circulation increased the residence time of deep water masses, the time elapsed between their last contact with the surface and their return to it, allowing oxygen consumption through decomposition to proceed further before replenishment occurred. The combination of high surface productivity, generating large quantities of sinking organic material, and sluggish deep circulation, providing inadequate oxygen replenishment, created persistent oxygen minimum zones, layers within the water column where dissolved oxygen concentrations were substantially reduced relative to surface and bottom values. Across much of the late Cretaceous ocean, in the western interior seaway, where the shallow depth and restricted geometry limited water exchange with the broader ocean, these conditions were particularly acute. Sedimentary evidence from the Greenhorn, Carlisle, and Niobrara formations records multiple intervals of bottom water anoxia preserved as laminated. Organic-rich dark shales deposited in the absence of the bioturbating organisms that normally disturb seafloor sediments and whose absence indicates oxygen concentrations too low to support their survival. The vertical structure of oxygen depletion in the seaway had direct consequences for the biological community. Organisms living in or near the bottom, benthic invertebrates, bottom-feeding fish, and the various organisms that depended on seafloor habitat, were the first affected by expanding anoxic conditions. As bottom water oxygen concentrations declined below the threshold for aerobic metabolism, these organisms either migrated upward into better oxygenated water or died in place, their remains contributing further organic material to the seafloor and accelerating the decomposition-driven oxygen consumption that had initiated the depletion event. The loss of benthic communities removed an important component of the food web, both as consumers of organic material that would otherwise accumulate, and as prey for mid-water and bottom-feeding predators, and altered the chemical cycling of nutrients in ways that could further affect surface productivity. For mid-water and surface-dwelling organisms, the immediate threat was not the bottom water anoxia itself, but the upward expansion of the oxygen minimum zone that accompanied it. As oxygen depletion extended from the sea floor upward through the water column, the habitable depth range for aerobic organisms contracted toward the surface. Large, active animals with high oxygen demands, fish, marine reptiles and sharks, require dissolved oxygen concentrations substantially above the minimum tolerable by less active organisms, and they would have been displaced from deeper water into the surface layer, as oxygen concentrations at intermediate depths fell below their physiological thresholds. This compression of the habitable water column into a shallower surface zone would have concentrated prey and predators alike into a reduced spatial volume, temporarily increasing encounter rates and predatory intensity before the longer-term effects of reduced prey availability began to dominate. The episodic nature of oxygen depletion events in the western interior seaway, documented as alternating organic-rich and carbonate-rich sediment layers reflecting oscillation between anoxic and better oxygenated bottom conditions, indicates that the system did not move irreversibly into permanent anoxia during the Campanian and early Maastrichtian. Instead, it cycled between stressed and less stressed states, with each anoxic interval representing a temporary deterioration followed by partial recovery as productivity fluctuated or circulation briefly improved. This cycling, however, was not without cumulative effect. Each anoxic interval caused mortality in benthic communities, disrupted nutrient cycling, and altered the chemical composition of the water column in ways that were not fully reversed during subsequent recovery intervals. The geochemical consequences of repeated oxygen depletion extended beyond the direct effects of low dissolved oxygen on aerobic organisms. In anoxic water masses, the absence of dissolved oxygen allows the accumulation of reduced chemical species, compounds that in oxygenated water would be rapidly oxidized and rendered relatively inert, but that in anoxic conditions persist and concentrate to levels that are directly toxic to aerobic life. The most consequential of these compounds in the context of the late Cretaceous ocean was hydrogen sulfide, a product of sulfate reduction by anaerobic bacteria that thrive in oxygen-depleted sediments and bottom waters, and that, in sufficient concentrations, is lethal to virtually all aerobic organisms through its inhibition of mitochondrial respiration. The presence of hydrogen sulfide in late Cretaceous marine sediments is documented through multiple geochemical proxies. Pyrite, iron sulfide, forms in sediments where hydrogen sulfide produced by sulfate-reducing bacteria reacts with iron in the sediment-poor water, and its abundance in the organic-rich black shale intervals of Cretaceous marine formations is a reliable indicator of sulfidic conditions at or near the seafloor during deposition. Biomarker molecules, organic compounds derived from specific microbial groups, preserved in these sediments include isorenieretane, a compound derived from green sulfur bacteria that require both light and hydrogen sulfide for their metabolism, and that therefore indicate the presence of hydrogen sulfide at depths shallow enough to receive light penetration. The occurrence of isorenieretane in Cretaceous marine sediments implies that at times during the late Cretaceous, hydrogen sulfide was not confined to the deep sea floor, but extended upward into the photic zone, into the sunlit surface layer where the base of the food web and the vast majority of marine life were concentrated. This upward intrusion of hydrogen sulfide into shallow water represents a qualitatively different and more severe threat to the marine ecosystem than oxygen depletion alone. While oxygen depletion compresses the habitable water column and stresses physiologically demanding organisms, the presence of toxic hydrogen sulfide in shallow water directly threatens the survival of organisms that cannot detect and avoid it quickly enough. Phytoplankton, unable to migrate away from toxic water masses, would have experienced direct mortality during sulfidic intrusion events, reducing primary productivity precisely when the food web was already under stress from other directions. Zooplankton and small fish, with limited mobility relative to the geographic scale of toxic water mass intrusions, faced similar mortality risk. The cascade upward from these lower trophic levels to the large predators dependent on them was a matter of ecological mechanics rather than speculation. A reduction in the prey base imposed by environmental toxicity rather than by predatory pressure. The evidence that hydrogen sulfide reached photic zone depths during at least some late Cretaceous anoxic intervals means that the deterioration of the ocean's oxygen budget was not a slow, distant process confined to the inaccessible deep sea floor. It was intruding, episodically, but with increasing frequency and severity as conditions worsened, into the very layer of the ocean that sustained all of the biological complexity and predatory intensity described in preceding chapters. The monsters of the late Cretaceous ocean were not facing an abstract or distant threat. The chemical conditions necessary for their survival were being compromised from below, incrementally, but with a directionality that the sedimentary record makes clear was not reversing. Hydrogen sulfide is among the most acutely toxic compounds encountered in natural environments. Its toxicity to aerobic organisms operates through a specific and well-understood biochemical mechanism. It binds to the iron-containing active site of cytochrome C oxidase, the terminal enzyme in the mitochondrial electron transport chain, blocking the utilization of oxygen in cellular respiration, even when dissolved oxygen is physically present. The result is a form of histotoxic hypoxia, cellular oxygen starvation, occurring not from lack of oxygen in the surrounding environment, but from the organism's inability to use the oxygen available to it. At sufficient concentrations, this mechanism produces rapid loss of function in oxygen-dependent tissues, with neurological and cardiac systems being particularly vulnerable due to their high metabolic demands. In aquatic environments, where hydrogen sulfide dissolves readily and distributes through the water column, the exposure of organisms unable to detect or avoid contaminated water masses is direct, and the physiological consequences are rapid. The natural production of hydrogen sulfide in marine environments is driven primarily by sulfate-reducing bacteria. Anaerobic microorganisms that use dissolved sulfate as a terminal electron acceptor in their metabolism in the absence of oxygen, producing hydrogen sulfide as a metabolic byproduct. Sulfate is abundant in seawater, and sulfate-reducing bacteria are ubiquitous in marine sediments. Under normal, well-oxygenated conditions, the hydrogen sulfide they produce is rapidly oxidized back to sulfate by reaction with dissolved oxygen or with iron minerals in the sediment, preventing its accumulation to ecologically significant concentrations. It is only when oxygen is absent or severely depleted, in anoxic sediment-poor water and in oxygen-free bottom water, that hydrogen sulfide accumulates rather than being oxidized, building concentrations that can eventually become sufficient to diffuse upward from the sediment and into the overlying water column. The rate of hydrogen sulfide accumulation in a given water mass depends on several interacting factors. The concentration of dissolved sulfate available for bacterial reduction, the abundance and metabolic activity of sulfate-reducing bacteria, the availability of organic carbon as an electron donor for that metabolism, and the rate of hydrogen sulfide removal through oxidation or mineral precipitation. In the late Cretaceous ocean, all of the factors favoring accumulation were operating at high levels simultaneously. Seawater sulfate concentrations, while variable across geological time, were substantial. Organic carbon delivery to the seafloor was high due to elevated surface productivity. The warm bottom waters provided thermal conditions favorable for high bacterial metabolic rates, and the weakened deep circulation reduced the supply of oxygenated water that would otherwise limit hydrogen sulfide accumulation through oxidation. The sedimentary record of hydrogen sulfide production in the late Cretaceous is preserved through several independent geochemical proxies that converge on a consistent picture of widespread and episodically intense sulfidic conditions in the bottom and intermediate waters of multiple oceanic basins. Trace metal enrichments in black shale intervals, particularly of molybdenum, vanadium, and uranium, elements that are preferentially scavenged from the water column under sulfidic conditions, provide a quantitative measure of the degree of sulfide development in ancient water masses. High trace metal enrichments in late Cretaceous black shales from the Western Interior Seaway, the Proto-Atlantic, the Tethys, and other basins indicate that hydrogen sulfide was not a localized phenomenon confined to isolated basins, but a feature of multiple major marine environments simultaneously. The sulfur isotope record from late Cretaceous sediments provides additional evidence for the scale of sulfate reduction occurring during this period. When sulfate-reducing bacteria process dissolved sulfate, they preferentially utilize the lighter sulfur isotope, leaving the remaining seawater sulfate progressively enriched in the heavier isotope. The sulfur isotopic composition of evaporate minerals and carbonate-associated sulfate, deposited during intervals of intense sulfate reduction, therefore shifts toward heavier values, recording the cumulative effect of widespread bacterial sulfate reduction on the oceanic sulfate reservoir. Isotopic trends in late Cretaceous sulfur records are consistent with elevated rates of sulfate reduction during the major anoxic intervals, though the interpretation of these records requires careful accounting for the multiple processes affecting sulfur isotope fractionation in marine systems. The spatial distribution of sulfidic conditions in the late Cretaceous ocean was not uniform. Restricted basins with limited water exchange, shallow epicontinental seas, semi-enclosed marginal basins, and areas where bathymetric barriers limited circulation were most susceptible to the development of persistent bottom water anoxia and hydrogen sulfide accumulation. The Western Interior Seaway, with its elongated geometry, relatively shallow depth, and restricted connection to the open ocean at its northern and southern termini, represents precisely the type of environment most vulnerable to the development of severe anoxic and sulfidic conditions. The sedimentary record from the deeper, more central portions of the seaway shows the most pronounced evidence of oxygen depletion and associated chemical changes, while shallower marginal areas show more variable conditions, reflecting greater influence from oxygenated surface waters and less accumulation of the organic material driving oxygen consumption. Beyond the western interior of North America, the Tethys Sea, the broad tropical ocean that separated the northern and southern landmasses of the Mesozoic world and that connected the Proto-Atlantic to the ancient Pacific, was simultaneously experiencing its own episodes of oxygen depletion and hydrogen sulfide development. The Tethys had been a site of recurrent oceanic anoxic events throughout the Cretaceous, and while the major events of the Cenomanian-Turonian interval were the most severe, the conditions generating them, high productivity, warm temperatures, sluggish circulation, persisted into the late Cretaceous and continued to produce localized anoxic episodes through the Maastrichtian. The biological communities of the Tethys, including mosasaur populations, diverse ammonite faunas, and the rudest reef communities described in earlier chapters, were therefore subject to the same type of intermittent chemical stress as those of the Western Interior Seaway, though the greater depth and connectivity of the Tethys provided somewhat more buffering against the most severe conditions. The upward migration of hydrogen sulfide from oxygen-depleted bottom waters into shallower portions of the water column, the process documented by the photic zone biomarkers discussed in the preceding chapter, was not a continuous or geographically uniform event, but an episodic phenomenon occurring during intervals of particularly intense oxygen depletion, when the rate of hydrogen sulfide production exceeded the rate of its removal by oxidation at the boundary between anoxic deep water and oxygenated surface water. This boundary, known as the chemocline, is typically a zone of intense microbial activity where chemolithotrophic bacteria oxidize hydrogen sulfide using the dissolved oxygen diffusing downward from above, producing a chemical barrier that under normal anoxic basin conditions prevents hydrogen sulfide from reaching the surface layer. When productivity was particularly high, when circulation was particularly sluggish, or when some perturbation temporarily reduced the efficiency of chemocline oxidation, hydrogen sulfide could breach this barrier and intrude into the lower portions of the photic zone. The green sulfur bacteria, whose biomarkers record these intrusion events, require both light and hydrogen sulfide, meaning their preservation in sediments indicates that the intrusion extended at minimum to depths receiving enough light for photosynthesis, typically the upper 100 to 200 meters of the water column, depending on water clarity. In a seaway with a maximum depth of several hundred meters, an intrusion reaching 100 to 200 meters represented a substantial fraction of the total water column and would have exposed mid-water organisms, including juvenile marine reptiles, fish, and the cephalopods and crustaceans forming the intermediate trophic levels, to potentially lethal hydrogen sulfide concentrations. The behavioral response of mobile organisms to chemical gradients in the water column is well documented in modern analogues. Fish and marine mammals detect hydrogen sulfide and other toxic compounds through chemoreceptors and avoid contaminated water masses when avoidance is possible. When the toxic zone is localized, when clean water is accessible nearby, and when the organism has sufficient time and locomotor capacity to reach it. In modern environments where hydrogen sulfide intrudes into shallow coastal waters, events documented in the Benguela upwelling system off Namibia and in other highly productive coastal upwelling regions, fish kills and mass mortality events result when intrusions are sufficiently large and rapid to prevent effective avoidance. The scale of even modern hydrogen sulfide intrusion events, which produce visible discoloration of surface water over areas of tens to hundreds of square kilometers, suggests that ancient intrusion events in the larger and more intensely anoxic late Cretaceous ocean could have covered substantially greater areas and persisted for longer intervals. For organisms with limited mobility or with life history, stages tied to specific depth zones, juvenile marine reptiles that may have inhabited shallow water, benthic invertebrates unable to migrate vertically, and the sessile or slow-moving components of the food web base, avoidance was either impossible or severely constrained. These organisms would have experienced direct exposure to sulfidic water during intrusion events, with mortality rates dependent on the concentration and duration of exposure. Repeated mortality events affecting specific life history stages or trophic levels would have had cumulative population-level effects that persisted beyond the intrusion event itself, reducing reproductive success, depleting juvenile age classes, and progressively reducing population sizes in ways that would not be immediately visible in the adult population, but that would emerge over subsequent generations as recruitment failure. The cumulative effect of repeated sulfidic intrusion events on the structure of the late Cretaceous marine food web was therefore not simply the direct killing of organisms during acute exposure episodes, but the progressive erosion of population viability across multiple trophic levels through repeated disruption of reproductive and early life history stages. A food web experiencing this type of chronic, episodic stress from below, from the chemical deterioration of the water column itself, while simultaneously under the intense predatory pressure documented in earlier chapters, was a system whose resilience was being depleted from two directions at once. The predatory intensity that characterized the system at its biological peak was not decreasing, but the chemical environment sustaining the prey base that made that intensity possible was becoming progressively less reliable, and the organisms that had evolved to thrive in conditions of high productivity and stable chemistry were increasingly confronting an environment in which neither of those conditions could be assumed. The question of which organisms possess the biological characteristics to survive within this chemically deteriorating environment, and which did not, is one that the fossil record addresses with considerable clarity, though the answers it provides are not always intuitive. Survival in a toxifying ocean did not require size, speed, or predatory sophistication. It required a different set of capabilities entirely, ones that the giants of the late Cretaceous had, in their long specialization toward maximum performance in a productive and stable ocean, largely failed to develop. Survival in a chemically deteriorating marine environment does not select for the traits that define success in a productive, stable one. The characteristics that allowed mosasaurs, large sharks, and plesiosaurs to dominate the late Cretaceous ocean at its biological peak, large body size, high metabolic demands, dependence on abundant and predictable prey, specialization towards specific ecological roles within a complex food web, became liabilities rather than assets as oxygen concentrations declined, hydrogen sulfide intruded into the water column, and the productivity supporting the upper trophic levels became less reliable. The organisms that persisted through these deteriorating conditions and that ultimately crossed into the post-Cretaceous world were those whose biological architecture contained features that, or often incidentally, rather than by direct selection for chemical stress tolerance, provided sufficient buffering against the specific threats the changing ocean presented. The most fundamental of these features was tolerance for reduced oxygen availability, hypoxia tolerance, a characteristic distributed unevenly across the marine fauna, but present to varying degrees in several groups, that would prove disproportionately persistent through the environmental deterioration of the latest Cretaceous and the subsequent extinction boundary. Hypoxia tolerance in aquatic organisms is achieved through multiple independent mechanisms. Increased hemoglobin oxygen affinity, which allows extraction of oxygen from water at lower concentrations. Reduced metabolic rate under hypoxic conditions, decreasing oxygen demand when supply is limited. The capacity for anaerobic metabolism, energy production in the absence of oxygen, which can sustain basic physiological function for extended intervals when aerobic pathways are compromised, and behavioral responses including vertical migration away from hypoxic zones and reduced activity to lower metabolic oxygen demand. Among marine vertebrates, elasmobranchs, sharks and rays demonstrate notably variable hypoxia tolerance across different species, with some demonstrating capacity for substantial metabolic depression under low oxygen conditions. The physiological flexibility of sharks, their well-documented ability to enter states of reduced activity and lowered metabolic rate, and their tolerance for a range of water chemistry conditions contributed to their survival across environmental deterioration events that proved lethal to more metabolically demanding or less flexible taxa. The survival of multiple shark lineages across the end Cretaceous boundary, while mosasaurs and plesiosaurs were entirely eliminated, is consistent with this interpretation, though it is important to acknowledge that the end Cretaceous extinction was driven primarily by the bolide impact rather than by the gradual chemical deterioration described here, and that survival across that boundary involved a distinct and more acute set of environmental insults. Bony fish, the actinopterygians, showed broadly comparable or greater hypoxia tolerance in many lineages relative to large marine reptiles, and the survival of numerous fish families across both the chemical deterioration of the latest Cretaceous and the extinction boundary itself reflects this physiological flexibility. Fish possess gill structures capable of extracting dissolved oxygen efficiently across a range of concentrations, and many species supplement gill respiration with accessory oxygen uptake mechanisms under hypoxic conditions. The small body size of most fish species, relative to the large marine reptiles, also reduces absolute oxygen demand, allowing survival at oxygen concentrations that would be insufficient to sustain the metabolic requirements of a multi-ton mosasaur. The relationship between body size and hypoxia tolerance is not linear, and large body size does not universally confer disadvantage under hypoxic conditions. Some large organisms have evolved effective hypoxia tolerance mechanisms. However, in the specific context of the late Cretaceous marine fauna, the energetically demanding lifestyle of the large apex predators, requiring sustained high food intake, frequent active swimming, and the maintenance of large body masses, created oxygen demands that made them more vulnerable to declining dissolved oxygen concentrations than smaller, less active, or metabolically more flexible organisms at lower trophic levels. An organism capable of surviving on infrequent meals, reducing its activity level dramatically during periods of chemical stress, and tolerating oxygen concentrations well below those required for peak performance, has a substantial survival advantage over one whose continued existence requires sustained high metabolic rates and reliable prey availability simultaneously. The crocodilians, whose persistence across the end Cretaceous boundary was noted in the earlier examination of Deinosuchus and its relatives, exemplify this combination of features with particular clarity. Modern crocodilians can survive extended periods of metabolic inactivity, tolerate a wide range of water chemistry conditions, including reduced dissolved oxygen, suppress their metabolic rate to a fraction of active levels during periods of environmental stress, and survive on infrequent large meals, rather than requiring continuous food intake. Their semi-aquatic lifestyle allowed them to access atmospheric oxygen directly through pulmonary respiration when dissolved oxygen in the water was insufficient, bypassing the dependency on water column oxygen that made purely aquatic organisms vulnerable to hypoxic conditions. These characteristics did not evolve as responses to the late Cretaceous chemical deterioration. They are ancestral features of the crocodilian lineage that had been present and functional for tens of millions of years. But they provided precisely the buffering that the deteriorating environment demanded. Turtles represent another lineage whose survival characteristics align closely with the demands of a chemically stressed environment. Marine turtles were diverse and abundant in late Cretaceous seas, and several genera persisted with relatively little modification into the Cenozoic. Like crocodilians, turtles breathe air and are therefore not dependent on dissolved oxygen in the water column for their primary respiratory needs. Their capacity for metabolic depression under adverse conditions is well documented. Some turtle species can survive extended periods of complete anoxia through anaerobic metabolism, producing lactic acid as a byproduct and tolerating the resulting physiological acidosis through buffering mechanisms in their shell carbonate. The ability to remain submerged for extended periods while maintaining minimal metabolic activity, combined with independence from water column oxygen, provided turtles with a degree of insulation from aquatic hypoxia that fully aquatic organisms could not match. Among invertebrate groups, the distribution of hypoxia and sulfide tolerance is complex and varies substantially across taxa. Certain bivalve mollusks possess notable tolerance for reduced oxygen conditions, including the capacity for sustained anaerobic metabolism and, in some species, limited tolerance for low concentrations of hydrogen sulfide through detoxification mechanisms involving sulfide oxidizing enzymes. The persistence of bivalve lineages through late Cretaceous chemical perturbation events, while ammonites, which lacked comparable anaerobic capabilities and whose calcareous shells were vulnerable to the acidified conditions accompanying anoxia, declined and ultimately disappeared, reflects this differential tolerance. Echinoderms, sea urchins, starfish, brittle stars, and their relatives show variable responses to hypoxic conditions depending on species and the severity and duration of oxygen depletion. Some echinoderm groups demonstrate reasonable short-term hypoxia tolerance through metabolic rate reduction, while others are highly sensitive to reduced oxygen and among the first benthic fauna to disappear from assemblages during anoxic events. The differential survival of echinoderm taxa through late Cretaceous perturbation events is consistent with this variable tolerance, with more hypoxia-sensitive groups experiencing localized extinction during anoxic intervals, while more tolerant taxa persisted. In the microbial realm, the domain of organisms whose metabolic capabilities most directly define the chemical conditions of the deteriorating ocean, the late Cretaceous provided conditions highly favorable for the proliferation of anaerobic and sulfide-tolerant microorganisms. Sulfate-reducing bacteria, thriving in oxygen-depleted sediments and producing the hydrogen sulfide that poisoned the overlying water, were themselves highly adapted to precisely the conditions they were creating. Green sulfur bacteria, which oxidized hydrogen sulfide using light in the photic zone during sulfidic intrusion events, formed dense microbial communities in chemocline environments where light and sulfide were simultaneously available. These microbial communities were not merely passive inhabitants of the deteriorating ocean, they were active participants in its chemical transformation, processing sulfur compounds, fixing carbon, and cycling nutrients in ways that both reflected and perpetuated the anoxic conditions developing around them. The concept of extremophiles, organisms capable of thriving in conditions lethal to most life, is typically associated with environments far outside the range of normal marine conditions. Hydrothermal vents, hypersaline lakes, acidic hot springs. In the context of the late Cretaceous deteriorating ocean, however, the relevant extremophiles were not exotic or geographically restricted organisms, but members of the normal microbial community whose metabolic capabilities positioned them to exploit conditions that were becoming increasingly widespread across what had previously been a productive and chemically hospitable marine system. Their proliferation during anoxic intervals was not a sign of ecosystem health, but of ecosystem restructuring, the replacement of the aerobic, productivity-driven biological community with a simpler, microbe-dominated system operating under fundamentally different chemical conditions. For the larger organisms, the fish, marine reptiles, sharks, and invertebrates that had constituted the biologically complex community of the late Cretaceous ocean, the expansion of microbial sulfidic communities represented the advance of an inhospitable frontier into previously habitable water. The chemocline separating oxygenated surface water from sulfidic deep water was not a static boundary, but a dynamic interface that migrated vertically with changes in productivity and circulation, sometimes deepening as conditions temporarily improved, more often shoaling as deterioration continued. Each upward migration of this boundary compressed the habitable water column further and increased the concentration of organisms dependent on oxygenated conditions, into a progressively smaller volume of surface water. The organisms that could survive this compression, through physiological tolerance, the behavioral flexibility, or independence from water column oxygen, were, in terms of the biological complexity and ecological diversity that had characterized the late Cretaceous ocean at its peak, a reduced and impoverished subset of the full community. The survivors were not the largest, the fastest, or the most ecologically sophisticated members of the original fauna. They were, in many cases, the most metabolically conservative, the most physiologically flexible, and the most capable of enduring the specific chemical insults that a deteriorating, toxifying ocean delivered. Their persistence was a function of traits that the most spectacular organisms of the late Cretaceous, the Mosasaurs, the giant sharks, the complex food web giants, largely did not share, and the divergence between what the deteriorating ocean demanded for survival and what its apex predators were biologically equipped to provide was not yet, in the Campanian and early Maastrichtian, producing the total collapse of those predator populations. The system was stressed, episodically disrupted, and progressively less stable, but it retained sufficient productivity and chemical habitability in its surface waters to sustain the large predators that depended on it. What changed as the Maastrichtian progressed, as sea level regression continued, as volcanic perturbations accumulated, and as the chemical deterioration of the deep and intermediate ocean extended its influence toward the surface, was the margin between the conditions available and the conditions required. That margin was narrowing, and its eventual closure would produce consequences visible across every level of the food web simultaneously. The disappearance of apex predators from an ecosystem does not typically occur as a single, discrete event. It proceeds through a sequence of demographic changes, declining reproductive success, reduced juvenile recruitment, increasing mortality rates among subadult age classes, and the progressive aging of the surviving adult population that may unfold across multiple generations before the population reaches the threshold below which recovery becomes demographically impossible. In the fossil record, this process is compressed by the resolution limits of stratigraphy and radiometric dating, making it difficult to distinguish a gradual multi-generational decline from a geologically rapid collapse. For the large marine predators of the late Cretaceous, the available evidence suggests that both processes were operating, that a measurable decline in diversity and abundance preceded the terminal Cretaceous boundary event, and that this decline was sufficient to have compromised the ecological integrity of the marine system before the bolide impact delivered its final and decisive disruption. The evidence for pre-boundary decline in late Cretaceous marine fauna comes from multiple independent sources that, while individually subject to various interpretive uncertainties, collectively describe a consistent pattern of progressive impoverishment in the upper trophic levels of the marine ecosystem through the Maastrichtian stage. Biostratigraphic analysis, the use of fossil assemblages to characterize and correlate geological intervals, shows a reduction in mosasaur species diversity through the late Maastrichtian relative to the Campanian peak, one with some genera disappearing from the record several 100,000 years before the terminal boundary. Ammonite diversity, which had been declining through the Maastrichtian in multiple basins simultaneously, reached a substantially reduced level in the final stages of the period, with only a handful of genera persisting into the terminal Maastrichtian from what had been a much more diverse assemblage earlier in the stage. The interpretation of these diversity patterns requires caution, because the fossil record is not a complete or unbiased sample of past biodiversity. The Signor Lips effect, the systematic tendency for the last appearance of any taxon in the fossil record to predate its true biological extinction due to incomplete preservation and sampling means that apparent pre-boundary disappearances of taxa may reflect sampling gaps rather than genuine biological extinction events occurring before the boundary. Correcting for this effect through statistical methods provides some reassurance that the diversity declines documented in the latest Maastrichtian represent real biological signal rather than sampling artifact, but the correction is imperfect and the uncertainty associated with it must be acknowledged. Setting aside the interpretive complexities of the biostratigraphic record, the ecological logic of pre-boundary decline in apex predators is straightforward and does not depend on direct fossil evidence of population reduction. A food web whose intermediate and lower trophic levels are being repeatedly disrupted by chemical deterioration events, the episodic oxygen depletion and hydrogen sulfide intrusion described in preceding chapters, will eventually transmit those disruptions upward to the apex predators dependent on those levels for their energy supply. The transmission is not immediate. Large apex predators with long lifespans and significant energy reserves can persist through periods of reduced prey availability that would be lethal to smaller, less buffered organisms. But sustained reduction in prey availability, persisting across multiple generations, will eventually produce measurable declines in reproductive success and juvenile survival that reduce the overall population trajectory below replacement. For mosasaurs specifically, the reproductive biology implied by their phylogenetic relationships and by limited direct fossil evidence suggests a pattern of relatively low reproductive output, consistent with their position as large, long-lived reptiles, combined with extended juvenile development periods during which young animals were vulnerable to both predation and environmental stress. Evidence from embryonic mosasaur material, though rare, indicates that mosasaurs gave birth to live young rather than laying eggs. A reproductive strategy that produces fewer offspring per reproductive event than oviparity, but invests more energy per offspring and results in more developmentally advanced neonates. This strategy, while advantageous under stable conditions, reduces the capacity for rapid population recovery following decline because the number of reproductive events and offspring produced per unit time is limited by the energy requirements of carrying developing young. The vulnerability of juvenile mosasaurs to the chemical deterioration of the water column was likely greater than that of adults. Juvenile animals of any species typically have less physiological reserve, narrower environmental tolerances, and reduced capacity for behavioral avoidance of stressful conditions relative to adults. A juvenile mosasaur of 1 to 2 meters in length, recently born and beginning to develop its predatory capabilities in the coastal and shallow water zones that likely served as nursery habitat, would have been substantially more vulnerable to episodic hypoxic or sulfidic conditions than a fully grown adult with large energy reserves and the locomotive capability to rapidly vacate deteriorating water masses. Repeated disruption of nursery habitat by chemical deterioration events would have produced elevated juvenile mortality rates that, accumulating across multiple reproductive seasons, would have progressively reduced the recruitment of new individuals into the adult population. The large sharks of the latest Cretaceous show a somewhat different pattern. While Cretoxirrhina, the dominant large shark of the Campanian Western Interior Seaway, had largely disappeared from the North American record by the late Maastrichtian, replaced by different shark taxa in the fossil assemblages of that interval. The broader elasmobranch fauna maintained greater diversity through the end of the period than the large marine reptile community. This differential persistence is consistent with the physiological flexibility arguments presented in the preceding chapter, but it also reflects the different reproductive strategies of sharks relative to marine reptiles. Many large shark species produce relatively small numbers of offspring, but invest substantially in their development, similar to mosasaurs. However, the physiological tolerance characteristics of elasmobranchs for variable chemical conditions may have provided sufficient buffering to maintain adequate juvenile survival even during deteriorating intervals, sustaining population viability when mosasaur populations were experiencing recruitment failure. The plesiosaurs, specifically the long-necked elasmosaurids that persisted alongside mosasaurs into the terminal Cretaceous, present a particularly informative case. These animals maintained presence in the fossil record into the very end of the Maastrichtian, with specimens documented from deposits very close to the terminal boundary in multiple geographic locations. Their persistence, while mosasaur diversity was declining, suggests that their ecological niche and physiological characteristics provided some degree of differential buffering against the stresses that were reducing mosasaur populations. Long-necked plesiosaurs, with their relatively small heads and presumed specialization toward fish and soft-bodied prey rather than large vertebrate targets, may have been less affected by the reduction of large prey biomass that would have impacted the largest mosasaurs most severely. Their foreflipper locomotion and likely more energy-efficient swimming relative to the tail-driven propulsion of mosasaurs may also have reduced their metabolic oxygen demands to some degree. The ammonites, whose diversity declined through the Maastrichtian, is among the most clearly documented pre-boundary trends in the marine invertebrate record, illustrate the food web consequences of apex predator decline, as well as constituting evidence of it. Ammonites had functioned throughout the Cretaceous as a fundamental intermediate-level component of the marine food web, prey for mosasaurs, sharks, large fish, and plesiosaurs, and themselves predators of zooplankton and small invertebrates. Their decline therefore represented both a symptom of broader food web disruption and a cause of further disruption through the reduction of prey availability for the predators dependent on them. This feedback, declining prey populations, reducing predator success, declining predator populations, altering the competitive dynamics among prey, altered prey communities changing the selective environment for the surviving fauna, is characteristic of food webs under sustained stress and is difficult to reverse once established. The physical changes to the seaway itself accelerated the ecological consequences of food web disruption during the latest Maastrichtian. The western interior seaway, which had been contracting through the late Campanian and early Maastrichtian due to sea level regression and tectonic uplift, had by approximately 68 to 67 million years ago fragmented into separate northern and southern basins, with reduced connectivity between them. This fragmentation reduced the effective range available to migratory large predators, concentrated populations into smaller geographic areas, increased local competition for declining prey resources, and reduced the genetic connectivity between populations that might otherwise have buffered against local extinction events through recolonization from unaffected areas. The geographic contraction of marine habitat was not limited to North America. The global regression of sea levels through the latest Cretaceous was reducing epicontinental seas worldwide, eliminating the shallow productive environments that had been among the most important habitat types for the large marine predators of the period. The Tethys Sea was narrowing as the African and European land masses moved toward convergence. The Proto-Atlantic, while deepening, was shifting from the shallow productive margins that had characterized earlier Cretaceous intervals toward a configuration more similar to a modern ocean basin: deeper, less connected to nutrient-rich continental margins, and less hospitable to the shallow water specialists among the late Cretaceous fauna. The cumulative effect of these converging pressures, chemical deterioration of the water column, reduction of prey base productivity and diversity, geographic contraction of optimal habitat, and the compounding demographic consequences of sustained recruitment failure, was a marine predator community that by the final stages of the Maastrichtian was measurably less diverse, less abundant, and operating within a substantially reduced ecological context compared to the Campanian peak. The monsters of the late Cretaceous were not simply waiting passively for an asteroid impact to end them. They were already in decline, already losing ground to the cumulative pressure of an environment that was systematically withdrawing the conditions their biological architecture required. What the bolide impact of 66 million years ago delivered was not the initiation of this decline, but its catastrophic and irreversible completion. A disruption of such magnitude and rapidity that the buffering capacity remaining in already stressed populations was overwhelmed simultaneously across all geographic ranges and all trophic levels at once. The impact winter, the collapse of photosynthesis, the acidification of surface waters through atmospheric sulfur injection, and the direct thermal and chemical consequences of the impact event compounded the existing stresses with an acute perturbation for which no biological preparation was possible and from which no recovery trajectory for the large marine reptile fauna was available. The ocean that survived the boundary was not a diminished version of the late Cretaceous system. It was a fundamentally reorganized one, structured around the absence of everything that had made the preceding system what it was. The apex predators, the dense intermediate trophic levels, the high productivity, and the extraordinary biological complexity that had accumulated across tens of millions of years of Cretaceous marine evolution. What remained, and what eventually gave rise to the modern ocean's own complexity, now emerged from a starting point of profound ecological simplicity. The end Cretaceous mass extinction, occurring approximately 66 million years ago at the boundary between the Cretaceous and Paleogene periods, represents one of the 5 largest extinction events documented in the fossil record, and the most recent interval during which the foundational biological structure of the global ocean was simultaneously disrupted across all major taxonomic groups and geographic regions. Its immediate trigger, the impact of an asteroid or comet, estimated at approximately 10 to 15 kilometers in diameter at the Chicxulub site on the present-day Yucatan Peninsula of Mexico, is established with high confidence through multiple independent lines of evidence, including the global iridium anomaly at the boundary layer, shocked quartz and impact spherules distributed worldwide in boundary deposits, and the direct identification and dating of the Chicxulub crater itself. What is less immediately appreciated than the fact of the impact is the precise sequence and relative contribution of the multiple physical and chemical insults it generated, and the degree to which those insults interacted with the already deteriorating conditions of the latest Cretaceous ocean to produce an extinction more severe and more rapid than either the impact alone or the preceding environmental stress alone would likely have generated. The initial physical consequences of the Chicxulub impact were essentially instantaneous on geological timescales. The energy released by the impact, estimated at several hundred million times that of the largest nuclear weapon ever detonated, vaporized the impactor and a substantial volume of the target rock, ejecting material into the upper atmosphere and beyond. The target geology at Chicxulub was particularly consequential. The impact site was underlain by thick sequences of carbonate and evaporate rock, limestone, dolomite, and sulfate-rich gypsum and anhydrite, whose vaporization released enormous quantities of carbon dioxide, sulfur dioxide, and sulfate aerosols into the atmosphere simultaneously with the physical energy of the impact. The sulfate aerosols were particularly significant for short-term climate effects, as they reflect incoming solar radiation and produce rapid surface cooling, the impact winter, that began within weeks to months of the impact and persisted for years to decades, depending on the injection altitude and atmospheric residence time of the aerosol particles. The collapse of photosynthesis during the impact winter was the mechanism through which the energy disruption at the surface propagated downward through the marine food web with lethal effect. Phytoplankton, dependent on sunlight for photosynthesis, ceased productive activity within the surface layer as light penetration was blocked by atmospheric particulates, the combination of dust, soot from impact-triggered wildfires, and sulfate aerosols reducing surface irradiance to levels insufficient for net photosynthetic carbon fixation. The duration of this photosynthetic shutdown is estimated based on atmospheric models constrained by the sulfur content of the target rock and the distribution of impact ejecta at months to years for the most severe light reduction, with partial recovery occurring over longer timescales as particulates settled and were removed from the atmosphere. For the marine food web, even a photosynthetic shutdown of months represented a catastrophic disruption. Phytoplankton populations, which turn over on timescales of days to weeks under normal conditions, would have collapsed within the first weeks of light reduction, removing the primary productivity base upon which all subsequent trophic levels depended. Zooplankton populations, dependent on phytoplankton for food, followed within weeks to months as their food supply disappeared. The cascade upward through the food web was rapid and comprehensive. Intermediate-level fish and invertebrate populations declined as their prey disappeared, and the large predators at the apex, already stressed by the pre-boundary deterioration of their ecosystem, faced the simultaneous elimination of the prey base that had sustained them. The ocean acidification resulting from the impact's atmospheric carbon dioxide and sulfur dioxide release added a chemical dimension to the biological disruption. Sulfur dioxide dissolving in surface water produces sulfuric acid, rapidly reducing ocean surface pH and creating conditions highly corrosive to calcium carbonate, the material composing the shells and skeletal elements of calcareous phytoplankton, ammonites, many bivalves, and other carbonate-dependent organisms. The dissolution of carbonate shells under acidic conditions would have affected the calcareous nanoplankton and foraminifera that formed the primary photosynthetic and secondary consumer base of the pre-boundary ocean, further disrupting the biological carbon pump and compounding the effects of light reduction on surface productivity. The calcareous nanoplankton, the coccolithophores, whose accumulated shells had built the chalk formations characteristic of the Cretaceous, experienced catastrophic decline across the boundary. Nanofossil assemblages immediately above the boundary layer in marine sections worldwide show a dramatic reduction in both diversity and abundance relative to the underlying Maastrichtian, with many species disappearing entirely and the surviving assemblages dominated by a small number of opportunistic generalist forms. This pattern, replicated across multiple ocean basins and in both shallow and deeper water settings, that indicates that the disruption was global rather than regional, and that it affected the entire photic zone rather than being confined to specific water mass types or geographic areas. The foraminifera, single-celled organisms that produced calcareous shells and that occupied both the surface plankton and the seafloor benthos, show a similarly dramatic turnover across the boundary. Planktonic foraminifera, whose diversity had been high through the Maastrichtian, experienced one of the most severe extinction pulses documented for any group in the fossil record, with estimates suggesting that 85 to 95% of species disappeared within the boundary interval. The surviving forms were predominantly small, simple, and morphologically generalized, the ecological equivalents of opportunistic weedy species that could persist on minimal resources during the post-impact productivity collapse, and that provided the biological foundation from which Paleocene foraminiferal diversity would eventually recover over millions of years. Ammonites, whose diversity had already been declining through the Maastrichtian, as documented in preceding chapters, did not survive the boundary event in any lineage. The last ammonite occurrences in the fossil record are from deposits very close to but below the terminal boundary, and no ammonite material has been confirmed from above it, despite intensive sampling in boundary sections worldwide. The combination of pre-boundary stress and the acute boundary disruption was sufficient to eliminate a lineage that had persisted through multiple previous mass extinction events across nearly 350 million years of marine history. The nautiloids, their closest living relatives, with a somewhat simpler shell geometry and different physiological characteristics, survived. A differential outcome that researchers have attributed to possible differences in egg and juvenile development strategies, habitat preferences, or physiological tolerance for the post-impact conditions, though the precise mechanism of this selective survival remains incompletely resolved. Mosasaurs disappeared completely at the boundary without any confirmed post-boundary occurrences in a global dataset spanning hundreds of fossil localities and multiple ocean basins. The finality of their extinction, the absence of any lineage, any population, any geographic refuge from which recovery might have proceeded, reflects both the comprehensiveness of the boundary disruption and the degree to which the pre-boundary deterioration had already reduced the demographic resilience of mosasaur populations. A population experiencing recruitment failure and declining abundance across the final millions of years of the Maastrichtian had less capacity to absorb the acute perturbation of the boundary event than a population at its demographic peak would have had. The margin between survival and extinction was narrower for late Maastrichtian mosasaurs than it would have been for their Campanian predecessors, and the boundary event eliminated whatever margin remained. Plesiosaurs, which had persisted into the latest Maastrichtian, as documented by their occurrence in boundary proximate deposits, similarly disappeared without survivors. Despite their somewhat greater ecological flexibility relative to the largest mosasaurs, the complete collapse of the marine food web's productive base removed the prey resources on which even the most adaptable plesiosaur populations depended. A long-necked plesiosaur capable of tolerating reduced oxygen conditions and surviving on varied prey types cannot survive in an ocean where the photosynthetic base has collapsed and the intermediate trophic levels sustaining its food supply have been simultaneously eliminated. The post-impact ocean was not simply a depleted version of the pre-impact one. It was an environment reorganized around fundamentally different conditions: reduced productivity, altered chemistry, disrupted circulation patterns, and a biological community stripped of the complexity that had accumulated across tens of millions of years of Cretaceous evolution. The darkness and cold of the impact winter gave way, over years to decades, to a greenhouse warming phase as the short-lived cooling effect of sulfate aerosols was superseded by the longer-lived warming effect of elevated atmospheric carbon dioxide from both the impact volatilization and the Deccan volcanic activity continuing through the boundary interval. This thermal oscillation, rapid cooling followed by extended warming, added further physiological stress to organisms already compromised by the productivity collapse and chemical disruption of the immediate post-impact interval. The recovery of marine productivity following the boundary event was neither rapid nor uniform. Evidence from carbon isotope records in post-boundary marine sediments shows a prolonged interval, estimated at hundreds of thousands to over 1 million years depending on the basin and the productivity proxy used, during which marine photosynthetic productivity remained substantially below pre-boundary levels. This protracted recovery reflects the time required for surviving phytoplankton populations to re-diversify and recolonize the global ocean, for nutrient cycling to re-establish through the recovery of zooplankton and other consumers, and for the physical and chemical conditions of the ocean to stabilize sufficiently to support sustained productivity recovery. During this recovery interval, the ocean was populated primarily by the surviving generalists, small fish, certain bivalves, surviving echinoderm lineages, sharks and rays that had crossed the boundary, marine turtles, and the microbial communities that had been proliferating in the deteriorating conditions of the latest Cretaceous. These survivors did not immediately occupy the ecological roles vacated by the extinct taxa. The niches formerly held by mosasaurs, large plesiosaurs, and the apex predators of the Cretaceous remained largely empty for millions of years, are filled gradually and incompletely by the diversification of surviving lineages into the available ecological space. The collapse of the late Cretaceous ocean was therefore not simply the termination of a biological community by an external catastrophic event. It was the culmination of a process that had been unfolding across millions of years, a progressive deterioration driven by the intersection of geological, chemical, and biological processes that had together systematically undermined the stability of the most complex and productive marine ecosystem the planet had yet produced. The asteroid delivered the final disruption, but it struck an ocean that was already compromised, already losing its biological integrity, already moving toward a reorganization that the impact event rendered instantaneous rather than gradual. The ocean that existed in the immediate aftermath of the end Cretaceous boundary event was, by any measurable biological criterion, a simpler place than the one that had preceded it. The physical ocean, its water, its chemistry in a broad sense, its circulation patterns, its thermal structure, persisted. Water continued to evaporate, condense, and move through the hydrological cycle. Sunlight continued to reach the surface layer. Dissolved minerals and nutrients were still present in the water column, available in principle to any photosynthetic organism capable of utilizing them. But the biological machinery that had processed those resources into the extraordinary complexity of the late Cretaceous marine ecosystem had been stripped away, and what remained was a collection of survivors whose collective ecological capabilities fell far short of reconstructing what had been lost, at least on any timescale shorter than millions of years. The immediate post-boundary ocean, the earliest Paleocene, the Danian stage beginning approximately 66 million years ago, is characterized in the sedimentary record by what geologists and paleontologists refer to as the Strangelove Ocean, a term reflecting the near-complete collapse of the biological carbon pump during the interval of maximum productivity disruption following the impact. In a functioning ocean, photosynthesis in the surface layer fixes carbon dioxide into organic matter, a fraction of which sinks to depth as organisms die, and their remains descend through the water column. With this biological pump maintains a measurable difference in the carbon isotope composition of surface and deep waters. Surface waters depleted in the heavy carbon isotope relative to deep waters because photosynthesis preferentially incorporates the lighter isotope. In the post-boundary Strangelove Ocean, this isotopic gradient collapsed, with surface and deep water carbon isotope values converging toward a common value that indicated the near cessation of significant biological carbon export from the surface layer. The duration of the Strangelove Ocean interval, the period of maximum biological carbon pump disruption, is estimated from carbon isotope records in multiple ocean basins at several 100,000 years, though the precise boundaries of this interval vary by location and by the specific productivity proxies used. This is not a trivial length of time in ecological terms. It represents many thousands of generations for the organisms that survived it, during which the ecological landscape of the ocean remained fundamentally impoverished relative to what had existed before and what would eventually develop afterward. The organisms that persisted through this interval did so not by maintaining the ecological roles they had held in the Cretaceous, but by existing at minimal biological activity levels, exploiting whatever limited productivity resources were available, and waiting, in the purely demographic sense of surviving and reproducing at low rates, for conditions to improve. The survivors themselves represent an ecologically disparate collection, united primarily by the characteristics that had allowed them to cross the boundary, rather than by any coherent ecological structure. Sharks and rays, represented by multiple surviving families, were present in the earliest Paleocene ocean, but at reduced diversity relative to the late Cretaceous, and without the large apex predator forms that had characterized the Campanian and Maastrichtian. The large Cretaceous sharks, Cretoxorhina, had already disappeared before the boundary, and the other large forms of the latest Cretaceous left no direct successors in the immediate Paleocene, were absent, and the sharks present in the earliest Paleocene were predominantly smaller, or more generalized forms whose ecological impact on the impoverished post-boundary community was correspondingly limited. Bony fish survived in greater diversity than might be expected given the severity of the productivity collapse, with numerous families crossing the boundary and providing the biological foundation for the subsequent Cenozoic diversification of teleost fishes into the ecologically dominant marine vertebrate group they represent in the modern ocean. The survival of so many fish lineages through the boundary event, despite the collapse of the food web supporting them, reflects a combination of factors. The physiological flexibility of many fish groups, the presence of refuge habitats in coastal and freshwater environments less severely affected than the open ocean, the ability of some species to subsist on alternative food sources, including detritus and benthic invertebrates, during the productivity collapse, and the rapid recovery of certain microbial and small invertebrate food resources that provided a minimal but sufficient nutritional base for generalist consumers. Marine turtles persisted through the boundary in multiple lineages and continued into the Paleocene with relatively limited taxonomic change, consistent with their semi-aquatic lifestyle and the physiological characteristics that had been identified as protective against the specific stresses of the deteriorating latest Cretaceous ocean. Their post-boundary ecology was presumably constrained by the same productivity collapse that affected other survivors, but their ability to utilize a range of food sources, including jellyfish, soft-bodied invertebrates, and marine vegetation, provided dietary flexibility that purely carnivorous predators dependent on specific prey types could not match. The modern sea turtle lineages are descendants of Cretaceous survivors, their evolutionary continuity across the boundary, a testament to the selective advantages of metabolic flexibility and semi-aquatic lifestyle under conditions of acute environmental disruption. Crocodilians, as noted in earlier chapters, survived the boundary event in multiple lineages and continued into the Paleocene and beyond. eventually giving rise to the modern crocodilian families. Their post-boundary ecology was necessarily terrestrial and freshwater focused in many lineages. As the marine environments they had occupied during the Cretaceous were reorganized and their prey base in those environments had been severely disrupted. The marine crocodilians of the Cretaceous, including the large forms related to Deinosuchus, did not persist into the Cenozoic in significant diversity, but the broader crocodilian lineage survived and continued to occupy semi-aquatic predatory roles in freshwater and estuarine environments, a persistence that, across geological time, allowed the group to maintain its ecological function even as the specific environments it inhabited changed. The invertebrate survivors of the boundary event provided the biological material from which post-Cretaceous marine ecosystems were constructed at their base. Certain bivalve families, surviving echinoderm lineages, polychaete worms, and various other benthic invertebrate groups persisted through the boundary and began recolonizing seafloor environments as conditions gradually improved during the early Paleocene. Their recovery was not simply a matter of repopulating existing ecological niches. The reorganization of the physical and chemical environment in the post-boundary ocean meant that the available ecological space was in some respects different from what had existed before, and the assemblages that developed during the recovery period reflected both the biological characteristics of the survivors and the new environmental conditions they were adapting to. The calcareous nanoplankton and foraminifera, whose near-total elimination at the boundary had been the most dramatic expression of the productivity collapse, began recovering in diversity through the early Paleocene, with new species appearing and diversifying into the ecological space vacated by the extinct Cretaceous forms. This recovery was not a restoration of the Cretaceous community, but the development of a new one, built from the surviving generalist forms and evolving rapidly under the selective conditions of the post-boundary ocean. The recovery of planktonic diversity is documented in exquisite detail in the sedimentary record of deep-sea cores spanning the boundary interval, where the transition from the impoverished assemblages of the earliest Paleocene to the increasingly diverse assemblages of the later Danian and Selandian stages is visible in the changing composition and abundance of fossil shells through the sediment column. The physical ocean itself was changing during the early Paleocene in ways that gradually created more favorable conditions for biological recovery. Global temperatures, after the thermal oscillation of the immediate boundary interval, began a long-term trajectory of change that would culminate in the Paleocene-Eocene thermal maximum approximately 10 million years after the boundary, a separate climatic event beyond the scope of this account, but that through the early Paleocene provided broadly warm and relatively stable thermal conditions conducive to photosynthetic productivity recovery. Sea levels, after the regression of the latest Cretaceous, stabilized and in some regions began to rise again as post-boundary conditions developed, gradually reflooding some of the continental margin environments that had been exposed during the latest Cretaceous regression and providing new shallow water habitat for the recovering marine community. Ocean circulation patterns reorganized during the early Paleocene as the thermal gradients driving circulation shifted with changing temperatures, and the removal of the late Cretaceous epicontinental seas altered the geometry of ocean basins. The development of new circulation patterns gradually improved the ventilation of deep water in some basins, reducing the extent of the oxygen depletion that had characterized the latest Cretaceous and providing more hospitable conditions for the recovering benthic fauna. And this improved ventilation was not uniform or immediate. Some basins retained anoxic bottom conditions well into the Paleocene, but the general trend was toward better oxygenated deep water conditions as the combination of lower surface productivity and gradually strengthening circulation reduced the oxygen demand on the deep ocean relative to the supply available through circulation. The ecological roles that had been held by the large marine predators of the Cretaceous, the Mosasaurs, the large plesiosaurs, the giant sharks, remained largely vacant through the early and middle Paleocene. No lineage immediately diversified to fill the apex predator niche in the post-boundary ocean, because the food web supporting an apex predator of that scale had not yet recovered to the productivity and complexity necessary to sustain one. The ocean was, in this sense, defined as much by what was absent as by what was present, an ecosystem with the physical capacity to support large predators, but without the biological infrastructure to do so, a gap that would eventually be filled over millions of years by the diversification of surviving lineages into new forms. The cetaceans, the whales and dolphins, were tens of millions of years in the future, their terrestrial ancestors not yet having made the transition to aquatic life that would eventually produce the largest animals in the history of the planet. The large predatory sharks of the Cenozoic, including the Otodus lineage that would give rise to Megalodon, were still early in their post-boundary diversification. The marine ecosystem of the early Paleocene was occupied primarily by organisms whose ecological significance lay in their role as the biological seed stock from which future complexity would grow, rather than in any immediate expression of the predatory sophistication that had characterized the late Cretaceous at its peak. What the fossil record of the early Paleocene ocean ultimately documents is not catastrophe alone, but the beginning of recovery, slow, uneven, operating on timescales that have no human scale equivalent, but genuine and directional. The emptiness left by the extinction of the late Cretaceous marine fauna was not permanent. It was a condition persisting across millions of years, during which the surviving organisms adapted, diversified, and gradually reconstructed a biological complexity that was different in its specific composition, but comparable in its ecological depth to what the Cretaceous had achieved. The ocean that exists today, with its whales, its large sharks, its diverse fish fauna, its complex invertebrate communities, is the product of that recovery, built across 66 million years of evolution from the impoverished but persistent biological community that survived the end of the most violent, most productive, and most biologically extraordinary marine world the planet has yet produced. The late Cretaceous ocean does not exist anywhere on Earth today. Its physical conditions, the warm, shallow epicontinental seas, the high productivity, the dense predator communities, are not replicated in any modern environment. It can be accessed only through the rock record, through the chemistry of ancient sediments, and through the fossil remains of organisms that lived and died in a world as remote from the present as any that can be reconstructed from physical evidence. But its legacy persists in the lineages it produced, in the evolutionary pathways it initiated, and in the biological architecture of a modern ocean that owes its deepest structural roots to the survivors of the world it became when its monsters finally stopped ruling the sea.